Welcome to the fundamentals of APIs. In this course, we're going to cover 4 key elements: the basics of APIs, the types or styles of APIs, testing and security, and then we're going to build an API from scratch. In the basics, we'll focus on protocols like HTTP and MQTT. We'll talk about the programming processes it takes to turn these designs into APIs, and we'll talk about the importance of connecting each API together using links and forms. We'll also focus on lots of different types of APIs, whether it's RESTful, RPC, GraphQL, Asynchronous, Hypermedia, Websockets, and Webhooks. Each has their own strengths and challenges. Each solves a unique problem and can come in really handy. We'll also talk about testing and security, so we'll focus on both happy path and sad path testing. We want to test the 200 OK as well as the 400 not OK situations. We'll also focus on security in the form of invitations, identities, and permissions, API keys, authentication, and authorization. Finally, we'll build an API from scratch using all the things we've learned in this course. We'll focus on design assets, we'll turn those design assets into code, and then we'll make sure that code is production ready to run. And that's how we're going to focus on the fundamentals of APIs. So, let's get started. Fundamentals of APIs, and in this module we're going to talk about the basics of APIs. And we're going to talk about the basics from 3 points of view. From the protocol point of view, how an API protocol works and affects the way we're going to design and build our API. From the programming point of view, the difference between programming the services that live behind the interface of the API and programming the API interface itself. And we're going to also look at the notion of connecting APIs together, what the details of the network are like, and how that affects the way we're going to design and implement our APIs. So let's jump right in to get to talk about HTTP in a nutshell. Now, even though we're going to be using a couple of different protocols, we're going to focus on HTTP in this module because that's the one we're going to be using most often. And we're going to look at it from 3 points of view again. That's messages, methods, and safety and idempotence. So messages is really what HTTP is all about. When you make a request, you send a message, and when you get a response, you also get a message back. So request and response is all about sending messages. Now this is what a request message looks like. You'll see that first line, which is called a start line, has 3 elements on it. It has a method, which we'll talk about in a moment. It has a URI, which is the resource or the target of our request. And then it has a protocol version, in this case, HTTP 1.1. You'll also see some name value pairs. These indicate other metadata about the request, and we'll talk a little bit about those as we move through the various versions of our API. Now, this is what a response message looks like. You'll see it also has a start line. Start line's arranged a little bit differently. It starts with the version of the protocol, and again, it's HTTP 1.1 in this case, along with a status code 200 and a description of that status, which is okay. We'll talk a lot more about status codes in a little bit. You'll see lots of name value pairs again, which is information the server is sending about the body of the message that you'll see at the very bottom of that message. There's some JSON that goes along. That's actually the part that most people focus on, that response. But there's a lot, as you can see, going on between the start line, the name value pairs called headers, and the body itself. Now let's talk more about those methods. Most people understand get, post, put, and delete as the methods of the HTTP protocol, but it turns out there are a lot more than that. Typically, you'll use get for reading messages and, for example, delete to remove a message from the server interface. Now, what's really important to understand is these method names are just that. They're names. They're strings, and they indicate an intent. When I send a get message, I intend for the server to get me information that's at the identified resource. Now, this is what a delete message looks like. It should look pretty familiar. It has a delete line, a start line, where it has the method, the URI, and the protocol, name value pairs. Then in the response, it has the 200 OK and lots of other information. So it's really no different than the get we were looking at before, except the few details like what that string is in the beginning. You can also use post to create new resources. This is what a post message looks like. You can see again, it looks very, very similar. It's got a start line, some name value pairs. What you can't see in this frame is that it also sends a body message along and then returns a message. Now, typically, as I said, post is used to create new resources on the service and put is used to modify, but that's really just by convention. In fact, you can use put to create messages and post to modify messages as well. So it's more about what your intent is and what you're trying to get done than it is about any particular format or standard way of talking about these elements. Now, as I mentioned before, there's a lot more than 4 methods. In fact, you can see from the screen here, it scrolls off the side, there are more than 40 different methods for HTTP, and new ones can be added at any time. So there will be lots of others that services will use frequently, even though we'll focus on just these 4 in this module. Now I want to talk about safety and idempotence because it has a lot to do with those methods. Safety means read only. It's safe to execute this function or make this request because it's only going to read data. And idempotence has to do with repeatability, that even if it writes data, it can be repeated safely. So safe methods are considered safe if they're defined as read only, and idempotent methods are considered idempotent if the intended effect on the server stays the same even if you execute it multiple times. Think about a delete. If I delete a record at URL 123, even if I send that delete 20 times, I'm only going to delete 1 record in the system, not 2. Now, get is read-only. That means it's safe. Put and delete are idempotent, which means they're not safe, but they can be repeated. What's really interesting is post is neither safe nor idempotent. In other words, when you execute a post, you're changing data. You might be, and when you're executing a post, you might be adding more than 1 record to the system if you repeat that same post. So, as a quick review of basics, messages are how HTTP work. We send requests and response, and we use the HTTP as a way of passing messages back and forth. Methods indicate the intent that the client would like the server to get, to read, to delete, to post, to put, and we use that method in these messages. Finally, reading and writing is really important because we're really talking about read-only and repeatability. And keep in mind that post is neither safe nor repeatable, and that will affect the way we design in the future. So that sets us up with the basics of protocol. Let's move on next to talk about how we program the difference between services and interface. All right, let's continue with our API basics and talk about the next step in the chain, and that's programming APIs. It turns out programming APIs and programming services are each unique in their own way, and it's when we put them together that they really work. So let's look into this a little bit deeper. So APIs are actually external elements. They expose a set of actions, such as read and write, or report, or share, and they take arguments as inputs, and they return messages as values, which might be a list of users or the computation of a value. So APIs are external. This is typically what programming an external API looks like. I'm using the Express platform, which I'll talk about a little bit more. And you can see that very first line in that function looks a lot like the start line that we were looking at just a moment ago in the HTTP protocol. It's got a method, get. It has a URL, which is the target of that get. That's here it's test. And then it acknowledges that there are request and response messages. Now, in this particular example, I'm not doing anything with the request message. I'm actually just setting up a response message with a header value and name value pair. We saw those before, and then just sending that message along. So that's the external interface. Now, services are internal. Services do the actual work of processing the arguments and the actions and composing the return values. Here's a little example of a simple math function that will perform an action like add or subtract or multiply or divide. It takes an action and two arguments and it returns a value. Now this, you can see, has nothing to do with HTTP. There's no method name, there's no return code, there's no message or of any kind. This is just the internal functionality. So what we need to do is we need to mix those APIs and services together. I use the Express.js format for doing this. There are lots and lots of platforms that you can use to mix your services and external interfaces together. This is what it looks like when I mix that read service request with the actual math service below. Notice that I get a get on read, and then I look at the request message and I look at the query values for the action and the values for X and Y. And then I load those into an arguments object and pass that to my internal service. I then get an answer from the internal service, put that in my message, and then send that message out. This is the real work of programming APIs. Taking in arguments at particular URI points, understanding the intent of the get or the post or the delete or the put, passing it into internal services to do work, and then formatting a message to get it back out. So we want to expose a set of arguments and actions and return values. That's the API. We want to process those arguments and actions and return values. That's the internal service. And it's when we mix them together that we're actually fully programming our APIs. Now that's the basic of API programming. Let's move on to the next step. All right, let's move on to the next step in our fundamentals of APIs. Now we're going to talk about connecting everything together. We've talked about the protocol of HTTP. We talked about the importance of programming, the difference between APIs and services. Now let's pull it all together in connecting things all together. So the first thing we want to talk about is API clients and the API services that they call. So consuming APIs is the real game, is the real action here. We know about the stack of services and APIs. Now we need to add to the stack clients, because clients are where it all happens. Clients call APIs, and it's the APIs that call services. So it's really important to keep that in mind. Just to kind of emphasize here, clients don't call services. Services are hidden behind the API interface, and that's why it's so important to design interfaces to match the client's needs. And we can be changing things behind the scenes as long as the client gets what they need. So it's all about clients connecting to APIs. Now, there are lots of different possible clients. The most common client is a browser client. So that's pretty easy to look at, and we'll take a look at that in just a second. But often you'll have command line clients or CLI clients or console clients. There are lots of versions of these kinds of applications. We'll take a look at one in just a second that can call the exact same API. Now, you may need a slightly different interface. In other words, that API may need to support more than one client interface, but it's still the API. It's still the connector to the service. And then finally, sometimes you need dedicated desktop applications for these elements as well. We need to dedicate our work for a particular API using a desktop application. So now let's take a look at a handful of examples. Okay, now let's dig in a little deeper into this notion of services and APIs and clients. So we've already looked at the service. Let's take a look at the client application a little bit. So one of the things we can do, we talked about this earlier, is we can really use just a command line client or a console client in order to do the work. So I have an example of a console client here, curl, and I wrote a little script that actually makes 3 different calls. We saw these calls earlier in another example. So I'm making the call to read, to write, and to subtract. And all I need to do to execute that is execute the script, and I get my answers back. Right? So that's pretty simple. That's pretty easy. So I can actually post, I can actually get my results. Now, maybe I want to write a little bit more sophisticated client. What I want to do maybe is write an HTML client, a browser client. So the first thing I need to do is I need to work up my browser application. And really, you take a look at this browser application, almost all of what I'm doing is in this markup is collecting inputs. So I want to say what the inputs possibly could be and what the values are. And then this line here actually calls the API. Now I'm using it at a different address. Don't worry about that. That's no big deal. But you can see I'm calling the write routine and using the post method. So what does that actually look like? Well, actually, let's look at the client right here. It should be pretty straightforward. I'm going to do an add for these two items. I'm just going to submit, and I get the answer of 20 back. Now, I didn't bother with reformatting the answer into HTML. I just left it as JSON, but you get the idea. Let's take a closer look for just a second here at this, and we'll take a look at making the same call again, only this time I'll have the little debugger running so you can kind of see what we passed back and forth. So when I do this time, I'll do a multiply, and I'll get a 100 back, and you'll see that the form data, the actual payload that I sent were these three values, and the response I got back was this JSON answer. So now I have a completely different client, and I have a different experience, but I have the same API. Now that's how we can keep clients and APIs separated, just as we keep APIs and services separated. So that's how we can pull it together and start to program not just the service APIs, but also the clients that use them. All right, so now we've seen some examples of connecting APIs to clients. Let's review our basics once again. We've talked about protocol, programming, and connecting in this module. So first of all, protocol is all about the idea of messages. HTTP uses messages in request and response back and forth. You need to invoke these things called methods, which are keywords that indicate your intention. I want to get something. I want to post something. I want to put something. I want to delete something. And we need to understand the relative safety and then that word idempotence, that ability to repeat each one of those methods. Can post be repeated? Can delete be repeated? Is put safe? Is get safe? That's all about the basics of the protocol. Now, we also talked about this notion of APIs and services. So APIs expose the arguments, expose the actions, and they provide return values in the form of messages. It's the services that actually process those arguments, perform those actions, and compose the return values that will be returned by the API. And we mix them together. We mix the services and the interface together in order to create a programmed API. And then, of course, we just talked about the idea of clients. Clients call APIs, APIs call services, and we have multiple kinds of clients that we can focus on. We'll be doing a lot of that in the next section. So that's the basics of protocol, programming, and connecting. Now let's start taking a look at all the various styles that we can use, all the various interfaces that we can use to expose services. All right, now in this module, we're going to focus on API styles. API styles are important because they indicate the design and the implementation details of your API. So we'll dive right in. What is a style? The values of styles. Why is it important? We'll actually briefly look at 7 different API styles that we'll dig into later. And then we'll review by just talking about how you select the style. How do you know you've got a good fit? So let's just start out with the simple thing first. What is a style? What do I mean when I say API styles? What I'm really referring to is the manner of doing something. This is the style we use. You've heard of management style, parenting style, all sorts of things like that. That's what I kind of mean. You can also think of style in a more artistic kind of sense, like pointillistic painting or Swedish modern furniture or Gothic architecture or punk rock. These are all styles. They have a relationship with lots of other elements that are very different, but they're all different styles of the same thing. So now let's talk a little bit about the value of styles. Why is it so important to have this notion of style? Well, it turns out it's your secret power. There are lots of ways to think about this, but probably one of the best ones is known as Maslow's hammer. If the only tool you have is a hammer, it's tempting to treat everything as if it were a nail. If you only know one style of APIs, whether it's REST or GraphQL
or anything like that, you may think that every API you build has to be in the same style, and that's often not correct. Usually you want to focus on what's most important, what's unique about that particular problem, and which style fits best. Because one size does not fit all. It's important to make a good fit. And goodness of fit or fitness is actually a pretty complicated way to think about this and decide, but a good definition is how well your model, which would be the way you're going to build and design your API, fits a given set of data, which would be the actions and the information you want to pass back and forth. If it's mostly about capturing events or capturing data or capturing actions, you're going to want to use an API that focuses on that fits well. And more importantly, you want to keep your options open. Knowing that you've got more than one style means you have more than one option, more than one opportunity. And this calls into mind Conway's delegation, which is an aphorism that says every time a delegation is made, a decision is made, alternatives which can be effectively pursued are narrowed. You have fewer options. Every time you decide something, your options narrow a little bit. So making a good choice now about a style will keep your options open in the future. So there's more than one way to get a good fit, and you always want to avoid the Conway delegation problem. So how many styles are there? What is a style that we should be talking about? I'm going to focus on 7 styles in this course, from async to Websockets. And here they are: asynchronous, GraphQL, gRPC, Hypermedia, RESTful, Webhooks, and Websockets. They each have a unique aspect to them. Asynchronous APIs are great when you want to focus on events, whether they're mechanical events such as like opening doors and windows or temperature gauges or things like that, or they're people like logging in and logging out and checking out of a shopping cart or something like that. Those are all events. If you want to focus on events, this is the one you want. However, you may want to focus on passing data or giving clients the ability to select their own data. Then GraphQL is really a great style for you. You may be focused just on the functionality such as save and delete and recall and submit and share and all those other actions. And those functions could fall under gRPC very, very nicely. There's also this notion of Hypermedia, which focuses on the connections between a customer and a company, and an invoice and a customer, and the products and the invoice. All the relationships become very, very important, and Hypermedia is a great style if you want to focus on that. That's opposed to a RESTful style, which focuses on the state of a particular resource, a particular customer, a particular invoice. If you're focusing on sharing the state of a resource, RESTful can be very, very powerful. Webhooks and WebSockets are also about asynchronicity, but they work a little bit differently. Webhooks is focused on one-way alerts where a client can subscribe to a server and get information. WebSockets is about two-way alerts where the client and the server can share information back and forth directly connecting to each other. So there are lots of possibilities there. What we want to think about is that each one of these is a powerful option. We just need to match them up. And then how do we do that? That means we need to select a style. We need to figure out which is a good fit. Remember, you want to stay focused on what your real problem, your real solution is going to be. Data-centric, resource-centric, event-centric, alert-centric, all those kinds of things. And that's really goes back to the same thing we talked before about how well a model fits the data. Now you already see what we want to do is fit our style to the problem we already have, not the other way around. And that means we need to weigh trade-offs. We're not always going to get the perfect fit. We're not always going to pick the best option because it just isn't available to us. And this comes to mind the notion of efficiency thoroughness trade-off from Eric Holnagel. And he says that corresponds to the need to be both responsive and to anticipate what may come in the future. Remember, there's the delegation problem again. So using the idea that we're going to trade off, we're not going to get a perfect fit every time, is an important thing to think about when you're picking a style. And finally, Tim Berners-Lee's rule of least power means we want to keep it as simple as we can. We want to use the least powerful solution for expressing the constraints and the program that we're working on. We don't want to get too complicated. The more advanced, the more complicated the solution, the fewer options we have, and we run into the delegation problem again. So there's lots of reason to think about picking the one that works the simplest, that trades off the good for the bad and is still a good fit. And that's where this all kind of comes together. So a style is the matter of doing it, how you're going to both design and implement your API. Your secret power is to keep in mind the value of styles, to avoid Maslow's hammer, to avoid Conway's delegation, and find that good fit. And we've got lots of possibilities that we're going to be able to explore to find all sorts of solutions that are going to be a good fit. And we're going to be able to weigh trade-offs and focus on the least powerful option that's needed in order to solve our situation and bring our API to the right place. That's the value of API styles. Now, let's dig into each one of them in turn and see how they really work in real life.
Okay, now let's dig into each individual style, explore them a little bit, understand their architecture, and then see a working example. And in this first one, we're going to talk about the asynchronous API style. Like I said, we're going to do this the same way for every one of these formats. We're going to start with the focus, the history, and the motivations, the basic elements of this API style. We'll dig into the architecture. In this case, for asynchronous APIs, we'll be talking about brokers and topics and subscriptions and channels. And then we'll have a working example that we can look at. So we'll be implementing an asynchronous API using the MQTT platform, which is a pretty popular platform, and one that's easy to get started when you're exploring. So for starters, let's start with the very basics. What is asynchronous all about? Where did it come from? And what are the motivations? So it turns out asynchronous APIs are really focused on events and event activities. That means originally it was aimed at connecting industrial devices that maybe do things like look for open doors, closed doors, monitor temperatures, or from the human perspective, know when someone's logged in or logged out of an application or checked out of their shopping cart or approved an invoice or something like that. The key element is, since it's based on events, it always talks about what has happened in the past. It never talks about what will happen. So someone logged out. It's not going to be someone is going to log out. Someone has already logged out, and so on and so forth. So it focuses on events initially for periodically connected. Sometimes they weren't 24/7, and it talks about the past. Now, the history of this asynchronous style goes all the way back to 1999 with MQTT at IBM. Some individuals were working to put together some kind of monitoring systems for major industrial devices, oil pipelines, big machinery, stuff like that. The AMQP platform came around 2003. That was a much more programmable platform than the original IBM MQTT. And ActiveMQ and RabbitMQ all come around the same time. Notice this MQ, message queue. Originally, the actual implementations had a lot to do with messages in queues that might collect up for quite a while and then be spooled out when somebody connected to that particular device. Nowadays, we actually don't use queues as much as we do just real-time data storage and processing. Now, as I mentioned, originally this was focused at low-power, rarely connected devices, SCADA devices they're referred to. There might be some devices that are out in the field that have some collection logging system, and then once a month someone would come by and plug in or use a wireless in order to connect to that device and spool things down. It's also used a lot in machine monitoring and automation, assembly and manufacturing, quality checks, and so on. That morphs into low latency real-time notifications like data changing alerts and things like that. And then eventually this high processing, almost streaming like delayed reply, large scale analysis kind of high volume processing. So asynchronous has a pretty long history. It's all talking about the past. MQT is just one of the various ways you can do this. And it's a lot of times works really well in low power, low latency, or high volume situations. Now, let's look at the architecture of typical asynchronous APIs and how that affects the way we would design, build, and monitor our services. I basically talk about these as broker-mediated communication streams. They pass messages based on topics or channels or tags you might see, and it's really focused on this notion of subscription and publication. So broker-mediated communication, what do I mean by that? There's a client that sends a message to a broker, and that broker can send a message to other clients. So in this world, everyone is a client, and some of those clients are actually brokers. Everyone can receive a message or send a message. It's just a matter of where they're sending them or who's sending them to them. Anyone can publish, anyone can subscribe. So this is not a hierarchical, not a client-server kind of environment. This will affect the way you think about how you're going to actually design and build that API. So there are messages and topics as well that allow publishers and subscribers to move back and forth. And those same publishers and subscribers can go back to the same broker and send other data as well. So it's all about the messages. Clients and send and receive these messages via the broker. There's the welcome message, the checkout message, the order received message, the approved message. There are all sorts of different kinds of messages. And the messages collect up into channels, or sometimes they're called topics. So all the welcome messages or all the checkout messages from all the different people. So that affects what kind of information you publish and what kind of information you can receive. So clients subscribe to a topic or a channel, one or more of them. I want all the welcome messages. I want all the orders received message. I want all the approved messages. And brokers distribute the messages to people who have subscribed to that particular topic, no matter where the message came from. So client A may publish a login message, but all these client Bs over here, they want to subscribe to that login message. So the client sends it to the broker. A key element to this design is the client knows nothing about the other subscribers. It only knows about the broker. That makes it very easy to modify the system. I can add brokers, I can add clients, I can add people who subscribe without disrupting the existing system. And that's very, very powerful. So we only need to know our broker and a broker communication platform. Every message has a topic. I subscribe and publish on topics, and clients tell brokers what they want to receive. And clients can change that at any time of day. People can continue to publish. They don't necessarily need to know who's subscribing. Okay, let's take a look at the pieces of this implementation of asynchronous services. First, we're going to have the hello service. The hello service actually is used by all of the API examples that we're going to be seeing today. And that just takes a few arguments and formats a welcome message. Then we have the publisher for the asynchronous API. This publisher actually connects to a broker and publishes messages out from that location. The broker itself is actually running remotely on an open source platform. Since this is just a demo application, we don't need to worry too much about security. So we're taking advantage of an existing broker out on the net. Otherwise, I might have to build one of my own. Usually in production, I'll actually build a broker system as well. And then I'm going to have a subscriber. So while somebody may be publishing messages, I'll be subscribing to those messages as well. And we'll take a look at what a message subscriber looks like in the asynchronous environment. All right, with all those pieces set and ready to go, let's go see how it actually looks in real time. All right, so here let's start our exploration of the async API. Take a little list here. What we're going to do is let's first load the publisher source code. All right, so this is all of the basic message publishing for our async API. You'll notice here we're calling the hello service. That's an external service. We're setting up the protocol for asynchronous APIs. In this case, it's MQTT. We've established a topic, and this is going to help us with generating some messages, both the location and the greeting. That's fine. Now, this is a really critical element. This is the broker. Remember, in asynchronous APIs, the pattern we're exploring is the notion of clients and servers are mediated by a broker. It's a broker-mediated service. We're going to use an external mediator. There's actually a test service called Mosquito at test.mosquito.org that we can use. Since I'm just doing a demo, I don't have to worry about privacy or security or anything. So I can publish messages to the test Mosquito server, and then I can also subscribe from there as well. So we'll connect that up. Now, what we're going to set up is, as soon as we do a connection, in this case, this server is every second it's going to publish a say hello message with the welcome topic. That's what this code is right here. The rest of this code is just how I generate the message. So this is my say hello function. It's going to generate some message, some timestamp, and some other things. And I'm going to pick some random greetings. It's not too much too exciting there. So now let's switch over to this window over here. And this time, let's load up the subscriber package. Subscriber package is going to do the same thing to start. It's going to connect to that Mosquito server, that mediator. So that's the broker. And it's going to say, I'm going to want to pay attention to welcome messages. So when I connect, I'm going to say, I want to subscribe to the message topic, which in this case is welcome. So I'll be listening for the welcome message at the Mosquito server. And every time the message shows up that matches my topic, I'm going to go ahead and echo that message out as a string. So that's pretty straightforward, right? So let's go back over here. And let's start out by doing an npm run publisher right here. So now it says it's running at the Mosquito server. What it's really saying is I'm connected and using the broker at test.mosquito.org. So now let's go over here and let's do an npm run and do that as a subscriber, right? So what this is going to do is connect up to that same broker and listen for messages. And sure enough, every second a message comes along that matches the welcome topic, and then I receive it, and then I publish it here. Now, this will go on as long as I want. Now, what's really interesting here, it's really important to point out, I'm going to go back over to the publisher side, and I'm going to stop the publisher. Now, you'll see that over here, there are no more messages being received, but there's no failure. There's no crash of this client application, even though this server is no longer publishing messages, because the broker is available. These two are talking to each other, and it just turns out there are no messages right now. I can go ahead and change that by restarting the publisher, and then sure enough, more messages start coming through on the subscriber side. So that's what it's like to set up an async API that uses the mediated broker pattern. All right, so that's how it looks in real time. Let's review what we were just talking about. So in asynchronous APIs, they're event focused. And they've been event focused since 1999. We've got lots of history, more than 20 years of history of doing asynchronous APIs. The architecture is a broker mediated pub-sub environment via topics and channels. That kind of puts in a nutshell all the things we need to think about. We need to think about brokers, publishers, subscribers, and topics or channels. It depends on which platform you're using to talk about that notion. And we looked at a working example. We used the MQTT platform to send welcome messages to subscribing brokers. And that's how we do asynchronous style APIs. Okay, now let's look at the GraphQL API style, a rather popular style right now. Just as before, we'll go through some basics, we'll talk about the architecture, and we'll explore a working example. Let's look at the focus, look at the history, look at the motivations behind GraphQL. GraphQL is focused on data. Data is the key, not functions, not resources, not actions, not events, but data. Every client request is actually seen as a data query. And these servers expose data stores as types, the customer type, the purchase type, the store type, so on and so forth. And then clients can send requests using a query language, graphical query language, and they can use types and filters and even arrange the shape of the response that comes back. And that's one of the unique elements of GraphQL. Now, GraphQL has a kind of a checkered history, a history that goes back quite a ways, even to the 70s, through a notion of query by example. Let me give you an example of what I want, and server, you figure out how to make the queries in order to give me the data that I need. So Moshe Zloof in the 1970s at IBM coined the notion of query by example. Now, we didn't really see a great example of this until Microsoft released a thing called Astoria in 2007, which became OData. We saw lots of other versions of query by example, but they were mostly just graphical interfaces. Microsoft's Astoria is actually a working server that understands the examples. The WC3 released another query by example type system, Sparkle RDF, in 2008, very close to the same time frame. And then it wasn't until 2013 when there was a new wave There was a thing called JSON API for Ember.js front ends, which used query by example and data queries as the functional interaction. And Facebook, now known as Meta, released GraphQL in 2015. So it's been around quite a while. Now we've gone from OData to GraphQL, basically. Open Data Astoria was created to make writing queries in code. So whether you were coding in their C# or VB or whatever, you could also code in Astoria. So OData was updated to support URL-based queries pretty early on, so we could start doing it over the internet, just not writing it in source code. Facebook picked up on this idea right away. GraphQL internally started working in 2012. JSON API in 2013, and 2015 is when Facebook Meta releases GraphQL. So we've got a long history here that dates back actually quite a ways, but is focused mostly in the recent 10 years or so. So GraphQL is all about data. It's all variations on query by example. Let me give you an example, and this is what I want back. And we really can trace it back to OData in the early aughts, all the way to GraphQL at Facebook today. So what does the architecture actually look like? It turns out the architecture on the front end, on the end between client and server, is pretty thin. Most of the activity, most of the action goes on behind the scenes. There's a client, there's a server, and they share a data model. So data models are defined using a schema definition language. This might look familiar to you since we've talked about various ways to define the interface using some kind of language. So SDL is schema definition language, and primarily it's types and queries. A type is like an object. You can see in the example the answer type, which has a who and a where member. Queries are sort of like functions, but they actually will be treated as a query element when you get to see them in a working example that we'll see earlier. So here, this query, there's one query defined, and that's the hello query that takes 2 arguments in and returns an answer back. There's also mutations, which allow you to update data, create data, or change data, and inputs, which are used as part of updates to define what are the inputs for changing information. We won't look at mutations and inputs today, but we will get a chance to look at types and queries. So servers expose whatever stored data they have through the schema definition language. They can expose queries as well as mutations. Queries are read-only requests, mutations are update requests. And servers use types and inputs to handle the arguments for either types for queries or inputs for updates. Now, the GraphQL language is really JSON. It's sort of a JSON query by example object. It'll make sense to you when we see the first example. Clients will use the schema definition language as a guide for crafting their GraphQL query statements. And GraphQL, as I said, is a kind of a query by example, but using JSON instead. And JSON is the response back as well. So SDL is the shared understanding between clients and servers. Servers expose stored data via SDL. Clients craft requests using the GraphQL statement language. So now let's take a look at a working example. Now, it looks pretty simple from the outside. We're going to start again with our hello service. We've seen lots of use of this hello service before. And then we're going to take a look at a server. The server actually implements several elements of the architecture, basically in this example in one place. There's going to be the schema definition language, the actual resolver, what they're called is resolvers to turn the query into a response, and then the actual interface for the web as well. And we'll take a look at each of those when we get to working. And the clients, we're going to show 2 kinds of clients. The first kind of client is this graphical client that comes sort of as a stock or standard GraphQL client. You can see that on the left, I've crafted a query, and on the right, I get the results. And that is a really query by example kind of approach. You can also use direct API calls using HTTP. So I'll show you an example of using the curl client for crafting API calls directly without a graphical interface. And that'll give you an example of what the results can look like as well. So let's go on to our example. Okay, let's go ahead and explore the actual code for the GraphQL version of the API. So for starters, let's load the index file. Now there's a lot going on in this index file. For starters, this is where we're actually publishing our schema definition language, or SDL. It says there's going to be a query type, which is called hello, which takes two optional arguments and returns an answer type. And this is what the answer type looks like. It is a who element and a where element. So that's our schema definition language that both the server and the client need to be aware of. Now, I've published a query called hello. That means I need a resolver for that query. I need to write code for the hello query that takes the two possible arguments and then handles them and gets a return value. We'll be using the hello service, the external service, just like we had in all the other applications. You can see that hello.welcome passing any args that are passed in and getting an answer back. Now that's fine. I've got the schema to share and I've got the resolver for that schema. I need to expose that so that others can use it. So I'm going to expose that over HTTP using a URL called GraphQL. All of the requests are going to go through the same URL over and over again. So that's what the actual service looks like. It's got schema definition, resolver, and exposes the API. Now let's go over here and take a look at the possible client applications here. All right, so what I did is I wrote a client application that uses curl, that uses HTTP to make the requests. So here's the first query request where I'm passing the who argument, asking for who and where coming back to me. The second one is where I pass an argument for who. And the third one is where I pass an argument for both who and where. So you can see it's a little dicey when I'm writing the data requests for post, but it's pretty understandable. Let's go back and take a look at what it looks like when we're running it. So what I'm going to do here is I'm going to start the service. All right, so there I've started the service. Now I can go ahead and test out my command line client over here by just running this little test script. And remember, I'm making 3 requests, one without arguments, one with one argument, and one with 2 arguments. And sure enough, that gets me the information I want back. So you can see here, this was the default with no arguments. This is when I pass in Mike, and I just get 1. And this is when I pass in both the location, and I get the who and the where. So that makes pretty good sense, but it's a little hard to understand. And it's really much easier if I take a look at it in a visual tool. This is the graphical tool that ships with most libraries of GraphQL. And it understands making requests to the server directly. So here I am making a request to the server without any arguments, and I get the data back over here. And I can go ahead and change that by making the argument says who is possible. So I'm going to do that and add Mike. And now I can make the request again, and you can see I get who and where back. So actually, what's really interesting is I can actually change this to say I only want to get the who back. This is where that query by example part comes in, and I'll get that back. I can even change the order if I want. I can get both of them back. And now I'll get where first and who. So I can actually use the SDL and use the graphical query language to say just how I would like this to appear when I finally get my answer over here. And that's all because I've written the SDL and the resolver, and I'm using the GraphQL library that was provided in this case by Express in Node.js, and that's how it knows how to use it. So that's how you can build and run GraphQL queries for your API.
All right, so let's review. Basically, GraphQL has been data focused since the 1970s. This notion of query by example, where we give an example of what we'd like the results to look like and let the server work out the details. The architecture is basically clients and servers sharing the data model. Now, it's important to point out that the data model that's shared is not necessarily the storage model. The data model could be a combination of lots of different storage, file storage, document storage, database hierarchical, and so on and so forth. But it's the one that's shared in the schema definition language that both the client and the server use. And we used Node.js to implement a simple graph service that exposed the welcome operations from data storage for both a graphical user interface and a command line API interface. And that's GraphQL.
Okay, let's talk about another API style, the gRPC style, or the Google Remote Procedure Call style. We'll talk about basics, architecture, and then look at another working example. And in the basics, as before, we're going to focus on the real reason for using this kind of style, the history behind it, and the motivations. So it's focused on functions. Basically, what we're trying to do is call a function on a different computer in a different memory space or address space, if you like. So we share function information together. That means we share the name of the function, any arguments that we pass back and forth, and any return value or object that you might get back. Now, we only need to understand that interface, that function name arguments in return. We don't need to understand the implementation. We don't need to know what language it's written in or what technical location it really is. We need to know how to reach it, but all we do is call it as usual. And this allows us to distribute work along a network. We can actually get lots of machines involved in doing this work. Now, this notion of remote procedure call has a long and storied history. Bruce J. Nelson coined the term in 1981, long before we were considered internet savvy. The Xerox PARC group implemented a version of remote procedure calling on an individual computer called the CEDAR protocol. That became the CORBA protocol in 1991. When we got the web, we got SOAP, which was Simple Object Access Protocol in 1998. And around about that same time, within a few years, Google had implemented its first RPC style, and it was internally called Stubby because they were little stubs. The interface was referred to as a stub, and it later was released as gRPC to the public in 2015. So it was initially implemented in mainframes. It was a way to get mainframe computers to work and talk together, to orchestrate them, really. Personal computing got us the C language in CORBA. That's basically coming not too long after the C language comes from Xerox PARC. So Java actually has a lot of CORBA implementations. The SOAP interface was very popular on all sorts of platforms. It was an XML interface. And the Stubby interface was originally XML, but eventually became JSON. Mobile is when we get the gRPC style. So we're sharing method signatures. This is the definition of the language we're sharing. We've got a long history from 1981 well into 2015. And it started in mainframes and goes all the way to mobile apps today. It is a very mature and very well understood style. Now, let's take a look at the actual architecture of what it's really like to set up a remote procedure call system. And there are three key components: the interface definition language, the shared understanding of that interface, the stub, and the client implementation of that interface, and the server implementation of that interface. So functions are shared via an IDL file, the actual signatures. And one of the most popular ones today is a protobuf file. This protobuf format uses this interface description language, which defines the service, the functions within that service, and the messages that are passed back and forth. Both the server and the client will use the information in this proto file, this protobuf file, to understand how they're to do their own implementation. And you can see in the example here, there's a welcome service. There's a little RPC function that's called say hello, which takes a hello request object and returns a hello reply object. And you can see below there those two objects, those two messages. The hello request has two arguments, and the hello reply has just one member as well. So this is the shared understanding between the two parties. Now, servers host an implementation of that function, the say hello function, and they use the IDL as a guide so that any incoming request for that hello function is sent through that interface to the local function. It's executed, and its results are returned back. So it's pretty straightforward. We don't really know what's going on. Is it hitting a database? Is it calling another function? We don't really care. All we know is that interface. Now, clients use the same IDL to craft their function calls to the service so that they know which service has which calls. Clients send arguments with the function, and they handle any return values. So there might be a welcome proto file that both the client and the server understand. understand. So the proto file or the IDL defines the service, the functions, and the messages. The servers host implementations of those functions, and the clients call implementation of those functions. So let's take a look at a working example of gRPC APIs using the protobuf format. Now, there are going to be a couple of steps along the way. We've talked about this earlier. We're going to be using the same hello service that we've used several times before. You probably have seen that already. We're going to look at the IDL file, the actual proto file that has that information in it that we were just looking at. We're going to look at the server implementation, what it takes to consume that IDL file and then expose that interface. And then we're going to look at the client implementation, what it takes to use that IDL file to know which functions to call and what arguments to send. Then we'll take a look at a little example. So let's go. All right, let's take a look at the gRPC version of this same API. Now, when we're in gRPC, as I mentioned before, we're going to define our interface in a separate document called the protobuf file. So here's our protobuf file that defines a welcome service that is one RPC call called say hello, which takes a request argument and returns the reply argument. Here's what our request arguments will look like. We've got up to 2 possible request values and 1 reply value. So that's pretty straightforward. Now let's take a look a little bit at the code. So let's look at the server, for example. So this is the real work, the say hello function. This is what we want to call. How do we wire that up to the interface using the protobuf file? What we're really doing right here is we're adding the protobuf file and saying we're going to expose the say hello functionality, and then we bind that to start the server. That's really all there is to it. We just need to connect to that protobuf file and then bind to that service. Now, let's take another look here at the client application. Client application is very, very similar. It's going to load the protobuf package file, and then it's going to connect and then start making calls to that exposed function, which is say hello. In the first example, we don't have any arguments passed. In the second example, we'll pass a couple of arguments along. So how does that look in real life? Let's go over here and we'll actually do a run server call here, which is going to set the server up ready and able to start accepting requests. So now let's just go up here and we'll do the same thing, npm run client. Now this will be the code that we saw down here below, which will actually connect up and then make 2 calls. The first one without arguments, the second one with arguments. And let's see how that looks. And there you go. Greeting hello world is the first one, and greeting hello you there is the second example. So that's pretty straightforward. We define our protobuf file, which tells us what our interface is. We expose that interface through a service, and we call that interface through the client application. That's how we define a gRPC API. All right, let's do a quick review. The gRPC style goes all the way back to 1981, and it's been function-focused ever since. It's very mature. The clients and servers share an interface definition, an IDL file. In the example we saw, it was called a protobuf file. And that helps servers implement the answer to the function call and the clients to know how to make that call. In our example, we used Google's RPC protobuf to invoke the remote welcome function and get its return values back and forth. So that's the gRPC style. Okay, continuing to dig into these various styles, let's focus on the RESTful style, one of the more popular API styles. Again, we're going to talk about some basics, focus, history, and motivations. We're going to talk about the client-server architecture and how RESTful uses that architecture to expose resources. And then we'll look at a working example of a RESTful API based on the same hello service that we've used in the past. So, what's the focus? What's the history? What are the motivations for this RESTful API? It's focused on the idea of resources. Every URL defines a resource. You describe your system in terms of resources, users, customers, orders, products, and so on and so forth. Initially, the whole point of RESTful architecture was to expose static documents like HTML pages or lists of information. However, with HTTP and HTML, it grew to a much more rich platform and expanded beyond documents to actually hosting applications. And again, these applications would either be the resource themselves or the applications would be exposed as a series of resources. Now, over the years, there were lots of versions of HTTP. I'm not going to go through each one of them, but I will point out, you'll notice that the very first version to version 1.1 took about 8 years, and then we worked on version 1.1 for over 15 years before we had a new version, which is version 2. And then within 7 years, we have a new version, which is version 3. Each one of these are pretty unique, but they all still work exactly the same. Code written for the 0.09 version of HTTP still works, like web pages and so on and so forth, still work in the HTTP 3.0 version. I find that pretty amazing. If you want to dig into the history a little bit more, 2 important documents I would recommend would be the initial proposal in 1990 that Tim Berners-Lee created for the World Wide Web and what becomes HTTP and HTML, and Roy Fielding's dissertation 10 years later, which really kind of wraps up the architecture and the sort of the engineering behind HTTP itself. Those are 2 very interesting and actually quite readable documents. As I said, initially it was designed for browsing documents. We would share documents in this HTML format. But by 1999, browsers were hosting sort of JSON-based message apps. We could send messages back and forth in the browser. By 2008, we get the Apple Store, which means we get rich mobile applications and RESTful client apps on the phone, which grew to quite an extent. And now we have quite a mix of documents, messages, and application approaches to using the RESTful system. So RESTful APIs are all about resources. They've been around for quite a while, and it's document style, message style, and application style all kind of mixed together, and that can sometimes be a bit of a challenge. So what is the real architecture of the RESTful API? Servers expose resources. Resources are formatted as documents. We'll talk a little bit more about that. And clients request those documents. So there's this client-server experience. Clients use URLs to figure out which resource they want to request, and servers return resource requests as documents. So if I say, please send me the weather today, the server will look up the weather and then format a document in HTML or JSON or XML or HAL or something and send that document back to the client. And that's how RESTful APIs work. Now, resources are formatted as documents literally means the responses are static documents. They look like static documents, even if they're generated on the fly. Clients receive these messages, and they could be in JSON or XML or HTML or a mix. HTML is actually a container format. Could have images, could have links, could have JavaScript, all sorts of things in the same response. So it's important for clients to be able to understand what format you're sending it. And there's actually a technology called headers. There's a content type header which says, this is the format of this incoming document. So clients can request documents from a resource. They always start the conversation. It's a client-server conversation. And clients can also send documents. So in HTML, those are seen as forms. So in this picture here, you can see this idea of sending a couple of inputs. The given name and family name are submitted to a resource using a particular HTTP method. That's a RESTful document that's being sent from the client to the server to modify something on the server. So every resource has a unique URL. Clients and servers share document formats. They both understand what JSON is or what XML is or what HTML is. And clients can update resources as well as read them. So let's take a look at a working example. We'll implement a RESTful API. Now, we've looked at this earlier. We're going to start with the same hello service that we've seen in all the other examples we've looked at. It just formats a welcome message. We'll look at the server, which waits, listens for requests on particular resource URLs, the welcome URL, for example. And then we'll look at the client application, which actually makes the call. And in this case, we're just going to use a command line existing HTTP client. We're not going to write a client. We're going to use an open source client that knows how to talk HTTP. So let's see how that looks. All right, so let's take a look at the REST example in real life. So there's a couple of things going on here. So first of all, this is the actual source code. This is a little bit of setup here in Node, and this is the work we need to do. We want to send a message around, and that message should have a variable, which is who. How are we going to get that variable? How are we going to be able to execute that function? Well, that's where our HTTP interface comes in. So in this case, we're going to listen on a certain port for requests, and those requests are going to be for resources. So this is the root resource, which returns the message with no answer in it. And this is the welcome resource, which is going to call this function that we have up above. And if I pass an argument, it'll return the argument. If not, it returns a default. So this is all there is to it. There's a little bit of functionality here, and then there's the HTTP interface there. Now, let's go ahead and move down here. Now, let's start our service. Node package manager start. So now the service is listening on port 3000. Remember I said before we were going to listen on a port. Now let's just go over here, just call up one of our options here, and we're just going to call this one service, which is the root resource. Let's call next the welcome resource. Notice the welcome resource actually gives us at least a default argument. We see that over here, what the default argument would be. Now we can also send our own argument. So I can say who equals Mike, and then that returns the resource with my argument added. Now there are a lot of other commands I can make. I can call, I can write data to the server, I can delete data from the server, but this is the basic process. What I'm really doing is taking functionality and defining that interface. And that interface is a resource that's put on a selected port. And that's how we create HTTP style interfaces. All right, so let's review what we've seen in the working example. So RESTful APIs are resource focused, and they've been that way since 1990. We've got quite a long history of understanding how RESTful APIs work. The architecture is client-server passing documents via resources. Resources are identified as URLs. Documents are identified as formats like XML, HTML, JSON, and so on and so forth. And we use Node.js to create a RESTful service that exposes the welcome resource to any client that wants to make its call. And that's a RESTful API. Okay, let's look at another API style, this one called the Hypermedia style. We'll take a look at the basics, the architecture, and implementing a working example of a Hypermedia API. Now, basically, Hypermedia APIs are focused on connections. Every client request starts with a link or a form, even if that link is typed in, but usually it's supplied by some document that's sent by the server. Servers expose messages that contain links and forms. Links are direct navigations. Forms allow you to send arguments. Clients find and use these links and forms to get work done, such as to navigate to a certain location, to filter out the data, to actually add or update a record in the system. Forms allow sending arguments with a link, and that includes URLs, protocol methods, inputs, and so forth. Now, there's a long and storied history with this notion of the Hypermedia style. Ted Nelson invented the word hyperlink in the 1960s. Doug Engelbart's Mother of All Demos, which is a great demo you should see, comes from 1968. You'll find it online if you just look up Mother of All Demos. And the real fun started when Wendy Hall released the Microcosm in 1988 for the British Library, followed very closely by Tim Berners-Lee's HTML the following year, which became really the basis for what we call today the World Wide Web. Now, it may have started with HTML in the 1990s, but there are lots of other message formats for using Hypermedia APIs: Atom Pub, HAL, Collection JSON, Siren, and in 2020, there was HTMX, a sort of an extension of HTML, which is very much a Hypermedia style approach to creating client applications that are very responsive. There are lots and lots of other formats as well that have been registered in the last 30 years. So Hypermedia APIs are all about the connections. When you've got lots of connections and lots of forms, this is a great, Hypermedia is a great style for you. Nelson's 1960s notion of hyperlinking documents grew into Tim Berners-Lee's HTML, which we all use today. And the last 30 years, we've gone beyond HTML with lots and lots of other hypermedia formats. So what's the architecture of a Hypermedia API? Basically, it's servers and clients sharing predefined message formats. Servers expose media types or messages that have links and forms. Hypermedia message formats are what the client and server share together, and clients select links and forms in these responses to get work done. So it's the server's job to encode connections and actions, links to various steps in a workflow, arguments that you pass back and forth, when you can delete something, when you can add something, when you can edit something. This is all described in documents that the server exposes. Hypermedia message formats, sometimes referred to as media types, contain the actions themselves in all of the descriptive details. It turns out there are only a few types of actions possible. One of them is called transcluding or transclusion. That's when you take data from another server and bring it to the client, such as an image or an iframe. You can also use a link to navigate from one place to another, take me to the search page. You can use a query form to read data, such as a search form. You add some arguments and you execute a search. Or you can do an update. You can use a method and URL to actually send arguments to write data to the server. Transclude, navigate, query, and update. That's what Hypermedia APIs are all about. And again, clients select the links and forms that they see in the response in order to navigate to where they want to go or in order to update the server with the information that they have. So process details and crafting protocol requests is really what client applications do. And clients use the ID and names on these forms, such as the client update form or the customer delete form, and so on and so forth, to tell machines what to do. So what does a working example look like? It's actually pretty straightforward. All our examples start with our hello service, and this one is no different than any of the others. We'll take a look at a Hypermedia server, one that knows formats and sends information encoded, actions and connections in that format. We'll take a look at the format itself. You can see here it's a simple hello message that has a few arguments and, in this case, a form that clients can use. And then we'll create a simple client application that knows what the hello format looks like and how to find and use the form in order to modify data on the server. So let's go. All right, so let's take a look at an implemented version of a Hypermedia API. And we'll start by taking a look at the server. Let's go ahead and zoom in on this here. So we've got several elements here. Here's where we call our service. Here's where we set up Express. We've talked about using Express several times. And here's the actual call to the external service. We'll work on that later. Here's the message format. This is actually the message that's understood by both client and server, and they can both use it to manipulate information back and forth. Then we'll set up a listener, and we'll handle calls. There'll be a call to either the root, which returns the working form, or a call to the form, which actually allows you to do a manipulation of the content. So we have the default root handling and the advertised form handling. Advertised by this href here that tells us that we can use the form to modify the contents of the message. Okay. So we've got that working. Let's go ahead and look over here at what the client looks like. We'll do the same thing. We'll zoom in here. So now we've got the client needs to memorize the very first URL, and we're just going to do this as a simple application here. And then we're going to know all the state information, the who data and the where data that we could use. And then we're going to actually manipulate the work. We're going to say call the root and call the form. So this is what calling the root looks like. We're going to make a request to that URL and send details and then get the response body and echo it. And then when it's time to fill out the form, we're going to call the form from the data, fill it out from our memory, and then make a request to send that modified information. Now, on the client side, what we're really doing here is we're implementing a kind of a tiny little HTTP or a tiny little hypermedia client. So whether it's a get, a delete, a post, or a put, these are the steps and the arguments we're going to send back and forth. Now, what's really great about this is I don't need to do much more on the HTTP protocol side. This is really all the details: get, delete, post, and put implementation. The rest is sort of understanding how to read forms and what's going to be in the form, and I can modify that as we go along. Now, let me go ahead, and we can always see already over here, the server is up and running. So with the server up and running, what does it look like when we make a simple request to see the message format? So let's take a look. This is what the message looks like right now. So if I just refresh this message here, this is what I'm going to get: the 2 arguments plus the form, which has details: name, href, method, and the arguments that I can pass. So that's pretty good. Let's use our own client application to run that. So we're going to run the client, and that's going to get the initial request, find the form, fill it out, and make that second request. Let's see what that looks like. Now, might be a little tough. It went by pretty quick. Let's open that up a little bit. So here you can see we started the client, it called the root, and it got the document, and from that document, it filled out the form and then made the request. So it actually filled out the information for the value Mike and Planet, and when the answer comes back, you can see it filled it out here. The answer comes back, the who and where has been updated, and it's ready for another update. And that's really all there is to creating a client that understands Hypermedia. The good news is if I change information, such as the URL or the method, then I don't need to change the client application at all. The client will follow whatever the form describes. And that's one of the big advantages of working with Hypermedia style APIs. All right, let's review what we've learned so far. Hypermedia APIs are connection focused and have been since the 1960s. We have more than half a century of experience in creating Hypermedia APIs. The architecture is based on clients and servers sharing predefined message formats such as HTML or HAL or Siren and so on and so forth. And we looked at a working example of implementing a Hypermedia API server and client using Node.js. And that's the Hypermedia API style. All right, let's look at another API style, this one called the Webhooks style. And as we've done before, we'll review some basics, talk about the architecture, which is a little bit unique. I call it a client-server-client architecture. We'll see why. And then we'll look at a working example of implementing a webhook API in JavaScript. So let's start with the basics. Webhooks is focused on one-way alerting, that is, sending an alert usually to what we call the client application. It's great for sending occasional notifications to client apps. Great examples are the code has been checked in, it's time to build, or it's time to deploy, or the customer just completed an order, it's time to ship it, or something like that. It's a very common use for triggering clients to do a particular action. But it's not very helpful for two-way communications. You can set up two-way webhooks, but it gets kind of confusing. If you want two-way communications, direct communications, we'll take a look at Websockets and we'll use that instead. However, webhooks is great for this one-way pattern. It was first described by Jeff Lindsay in 2007, so we've got lots and lots of years of experience in figuring out how to use and integrate webhooks into our existing applications. One of the great things I like about webhooks is that it's over HTTP, but it is point-to-point messaging almost in real time. So that's pretty handy. As I've said, it's grown in popularity to help update web apps over simple HTTP, including client applications like mobile apps. And DevOps tooling uses it quite often to trigger different things going on. So a client tells servers where to send messages. And that's basically what the hook is. The hook is, here's a URL, send me messages here whenever an event occurs. And then webhooks actually replace the need for constant polling by clients. So clients don't have to keep saying, do you have something, do you have something, do you have something? They just simply say, hey, when you get something, let me know. So webhooks are great for sending occasional notifications to clients. They were first described in 2007, and they basically are the process of telling servers where to send messages when an event occurs. So let's take a look at the architecture, how this really works out. As I mentioned, clients register a hook. Clients send a receive URL or use this URL when you're sending me messages when they send that to the server. They may also send in more complex or involved webhook systems. They might send a filter or topic bit of information. In other words, if you get an information about welcome messages, send me that information at this URL. So clients share a URL with the register server. Servers then log that URL or that hook for future use. Often they just keep a list of clients that are available, and that list may be in memory, it may be kept on disk for persistence, it doesn't really matter too much, but servers remember which clients to alert whenever a certain event occurs. And when that event occurs, the server then sends an alert message using the URL to all the clients in a list that are listening for that particular message. Now, this may sound an awful lot like mediated messaging, but it's really point to point, and that's an important difference with webhooks. So let's take a look at a working example. Let's review quickly here. First of all, as we've done in all our other examples, we'll start with a hello service. We're going to be using that service for all of our examples. And then we'll take a little bit of time to look at the alert server, the server that receives requests from clients, memorizes that request, and then sends out messages whenever an event occurs. And then we'll have a couple of clients. We'll have a client A application that sends out a registration and then listens for messages. And then we'll also take a look at a client B that does the same thing. Really, they're both the same bits of code, but it's just to show you that there are more than one cases that we can send to. So let's go take a look at the live code. Okay, let's take a look at the code in our webhooks server and client setup. So to start, let's look at the server code. So there's our first call to the hello services, loading some other libraries and some random information that we're going to use to create messages. Now here's the loop that sends alerts to clients that have registered with us. We'll take a look at how that happens here next. So here it is. This is how a client registers with this server. It sends a post to webhook with a URL, and that URL gets put into an array, and then we'll use that URL when we send out messages. Then we just sit there and listen for those registration messages. And here's the code that actually sends the alerts. So right here is where we take the list of anybody who's registered, and we go ahead and take a message, and we post to that URL the body message, which in this particular case is actually just the welcome information that we've talked about before. That comes from say hello. That's right up in here. So this generates a random greeting message, and then this uses the list of registered clients in order to send that message out. All right, so that's the first step. So now let's take a look over here at a client application. So the client application knows what the registration URL is because it's going to have to register when it starts up. And then it has to share with the registration URL this client's URL for listening to messages. So it's important for the client to know both the registration URL for the server and the listening URL for this client. So the first step is to register a client. Let's jump right down to where we register that client here. And then again, it's sending a post message to that server URL, and it's sending the URL of the client application. That's really all it is to it. You could also send a filter message or some additional tracking data, but for our case, we're just sending the URL. Then we need to set up a listening post, a listening event, for every time that server does send an alert to us. So that's what this event is. Remember, we told the server this URL is the event resource. Here's the event resource that accepts a post, and it says, hey, we got the message. It'll actually just echo the message out for our particular cases, but in this case, I might use the message to go ahead and start a build or close out a customer's account or notify them that it's shipped or on the way, so on and so forth. And then all we really do is just, in this case, we're just waiting for that particular alert to come through this client application. It just waits for the alert and then does what it's supposed to do every time we hear the alert. So let's take a look at how this really works in real life. So let's start down here. We're going to start up the server. Now this server is going to be monitoring activity, and you can see it actually sends out alerts on a regular basis. We've just done a loop that says every 2.5 seconds, send out a welcome message. This could mimic, again, people logging in or orders being completed or someone finishing a check-in in source code that needs a build or a test run or something like that. For now, we just have it send out messages on a regular basis. So now let's take our client application. We've got a copy called client A, and we're just going to run the client application. The first thing it does is it registers, it sends their registration, and then it waits for events to happen. And as you can see, event notices are being received, and they match the sending message from the server application. Now, just to make a complete cycle here, we can actually register a second client that listens to those same messages. Maybe one client does one set of tests, another client does another. There's a lot of possibilities here. And again, it's going to register its own event URL. You can see I echoed the array of the event URL. That's not normally how you do it. I just do that for this demo so you can see that it's registered. And now they're all receiving notifications. And this is the work of webhooks. Webhooks servers, webhooks client applications, servers sending out alerts after registrations, clients registering and then waiting for that information. And that's what webhooks looks like. All right, let's review what we've learned today. So the basics of webhooks is that they're triggers for client applications, and they've been happening since 2007. There's a unique client-server-client interaction. Clients register a URL for the server listens for triggering events, and when it happens, sends a message back to the client using that URL. And we looked at a working example in Node.js where we implemented both the registration server and the client applications that receive alerts on occasion. And that's implementing webhooks. All right, let's talk about the Websockets API style. And along with the basics, we'll take a look at the architecture and a working example of implementing a Websockets API. So what's the focus, history, and motivations behind this particular style? Well, it's focused completely on two-way communications. It was designed to support what we call full duplex or two-way comms between two parties. So while you'll hear me say client and server, really it's peer-to-peer, and we'll explore that a little bit more. It's commonly used for chat apps and other conversation-style interfaces, whether that's with a chat bot or multiple individuals on a Discord channel or some other kind of chat channel. It's very similar to the MQTT-mediated asynchronous API style that we've talked about here, but it has no mediators. There is no central location at all. There's a long history of this kind of full duplex communication. Java applets, which were plugins for browsers, did full duplex in the 1990s. A technology called pushlets was released in 2001, and that morphed into a thing called Comet, named by Alex Russell in 2006, which was a kind of multi-peer-to-peer style. WebSockets were defined for HTML5 by Ian Hickson and Michael Carter in 2008, and finally, WebSockets gets its own WebSockets protocol standard in 2011. So you can see there's been lots of activity over the next 2 decades. And it really is peer-to-peer to peer to peer to peer. Clients open connections to servers. Basically, someone opens a connection to somebody else. Peers can send and receive messages back and forth. You don't have to wait for anything. There's no response to a particular message required. You can talk anytime you want. Peers can also close connections anytime they want and reopen connections anytime they want. They don't necessarily have to persist over time. So WebSockets are designed for two-way communications. They've been doing this kind of thing since 2001, and clients open connections to servers to send and receive messages back and forth in a peer-to-peer style. So let's take a look at the architecture and explore what that peer-to-peer really means. So servers connect to clients. Clients open a connection. Servers accept those connections. Servers can handle multiple connections from many clients and actually keep them separate so they'll know which conversation is going on and how to answer each individual client. Clients can also open connections to many servers. It kind of doesn't matter. The notion of client and server really disappears when you have this kind of peer-to-peer connection service. So as I said, anyone can send and receive messages. You can initiate a conversation. You can send data information. A lot of times, this kind of technology is used to monitor machinery, equipment, and send out status messages. It could be used in driving directions. It can be used for controlling robots, lots and things like that. The message format is totally wide open. It's usually JSON nowadays. It originally was XML, but it can be anything you want, including just plain text. And again, all connections are direct. There is no mediator that's not designed for communications with a central server like MQTT async is. Peers need to keep track of their own connections. Now, it's built into almost all the libraries to be able to do this relatively easily, but it's your job to do that work. Now, some implementations do mimic mediators. In other words, everybody connects to a chat server, but that's just because of the way it's implemented. Now, it's worthwhile to take a look at this picture. You'll notice that in this example, peer A has connections to peer B, C, and D. You'll notice that peer B has connections to A and C, and that peer D has connections to C and A. But peer B and peer D do not have a direct connect. They cannot talk directly to each other. So the actual topology of the arrangement of the network is pretty important. So let's look at what it takes to implement WebSocket APIs. So let's do a quick review. We'll have our hello service, the same hello service we've used for all our API style implementations. I've implemented a workflow server as one of the peers. This workflow server keeps track of the status of a particular job and advances that status when it's necessary. And then I've implemented a process client peer, which actually pays attention to the status of a job and performs work based on that status. I've also added a traffic monitor application that's built in HTML for a browser. This just watches the traffic go by step, so you can see how a browser version of WebSockets works as well. So with that in mind, let's go. All right, let's take a look at what it's like to implement a WebSocket server and client. So we'll start by looking at the server code. Server code's pretty simple here. Let's zoom in a little bit and just take a look at it. The basic loop here is we get an instance of a server on a port, and then we wait for connections. And when someone connects, then we can listen for messages that they would send. In this case, we're listening for a data message from our client processor. We're going to check the status, and we're going to update the workflow status, and then we're going to broadcast that information to any client that's connected. Now, that's a really important step. This is our chance to broadcast information to a wide set of connections. Now, the workflow is pretty simple. In this case, we're just going to change the status of a record, and that will allow the client process to continue on. It would be more involved if we were actually doing some processing work on an assembly line or something like that. But this gives you the basic idea of what it's going to be like. So let's go ahead and move over here to see what the client is going to be doing. The client's actually going to do a bit more work. Let's go ahead and zoom in. Same thing, we're going to get an instance of our WebSocket server. And we're also going to get an instance of our hello service, right? We've been using the hello service throughout the series. So we start up the server, we wait until it's open. Once it's open to our connection, then we're going to say, all right, let's get an initial message. Let's send that initial message along. Let's wait until we receive a message. Once we receive a message, that means that the server's probably changed the status of the work. I can update that status using this update message function internally, and then send that back to the server. The internal functionality looks a little bit more interesting. We're going to generate that initial message up here the same way we did in all the other versions of our API using that hello service. And then we're going to perform work. We're actually, in our case, we're just going to modify the contents of the message a little bit with random greetings and location values depending on the status that's been set in the message. And that's really all we're doing here. This is just a chance for us to get a sense of what it's like to start interacting with both server and client. So let's go ahead and move down here, and we're going to actually run this server. So the server's going to get started. Now the server's waiting to see what happens. It's waiting for a message from the work client. So now we're going to run the client. And remember, the client is going to initialize a message and then start responding to any status updates. So there we go. We're going to start seeing messages run across the screen here. And each step along the way, there's a change in status. Now, this is really what's going on. This is an interaction between the two. Now, what's really interesting is I can connect another client to this same server to monitor what's going on in the workflow. And that's what's going on over here in our browser window here. If I just refresh this, it's going to connect, and then it's going to see which messages are moving through the system. So waiting, working, complete. So there's a cycle there, and it monitors over and over again. Now, we hadn't had a chance to look at this particular client. Browsers are particularly tuned to this idea of WebSockets. I don't have to write very much code at all in order to connect to monitor this service. All I really needed to do is connect to that workflow server on the same port the workflow server was advertising. And then every time there's an open or a message or a close instance, I can update my screen. Here I'm just doing some intertext on this pre-code here. And that's all that's really happening here. So it just continues to monitor the status. So there you have it. That's really the basics of a WebSockets system. A server, at least one client, and they can send messages directly back and forth. Now, one of the things I can do here is I can actually stop the client application. You'll notice that the connection has been closed over here on the server. The server knows that connection has been closed. Now, if I close the connection on the server, then we're going to notice that our client monitor is also closed as well. So we've kind of completed the loop. And that's handling a WebSockets server. All right, let's review what we've discovered. WebSockets have been full duplex since the early 2000s. Two-way communications, real peer-to-peer technology. And that's the architecture focus. It's direct connect between different parties, not mediated in any way. That's got both pluses and minuses that you'll need to deal with. And then we used Node.js to implement a WebSockets server and a set of clients that both interacted and monitored the traffic activity in the network. And that's the WebSockets API style. All right, let's talk about testing your APIs. First, we'll cover the goals of testing APIs. Goals are slightly different than testing code, and we'll see why that is. Then we'll talk about using SRTs, or simple request tests approach, to validate your APIs with a simple, scriptable, storable set of tests that you can repeat over and over again while you're coding. And then we'll look at a working example of testing an API using SRTs in action. So let's start with the goals of API testing. So we want to take an outside-in approach. Consumers, remember, can only see the API. They can't see the code behind it. They don't know what you wrote it in. They don't know what the database looks like, or how many components there are, or how many other services are behind this API. All they know is they have an API. So that's what our tests are going to focus on. Our aim is to test that interface itself, not the code behind it. Somebody else is going to need to do the code, or we'll do the code in different kinds of tests. Again, we're going to focus on validating resource inputs and response outputs. We want to confirm that the URL actually exists, that it actually has some kind of response, and that the response from that URL is expected. It's in the right format, it contains the right elements, and so forth. We also want to validate the methods, the use of get or put or post or delete. We're going to validate the input parameters, both the query input parameters and the body parameters for, say, post or put. And again, we want to check those response bodies, make sure it's the expected body in the right form with the right elements inside. Essentially, we're confirming interface behavior. We want to validate the expected behaviors on all fronts, and that includes not just the 200 OK examples. What does it take to actually save a record or modify a record, but also the SAD path, or the not OK, or the 400 or 500 requests. where I'm not allowed to create this record unless I have the right number of arguments or the right type of arguments, or they're in the right order, and so on and so forth. So both happy path tests, 200 okay, and sad path tests, 400 bad request is usually the case. So we want to take an outside-in approach for the consumer's view. We want to validate the interface, not the code, and we're going to include both happy and sad path testing. So let's talk about this notion of simple request tests, or SRTs, to validate your API. Simple request tests are designed to probe the interface. In fact, that's all they can do. They can confirm that the URLs you know about respond. They can include request parameters such as the body and the URL request parameters, and they can validate an OK and a returned resource. As you can see from this list here, this is a script of happy tests. It's a series of URLs with different methods and different bodies. There's even one at the end that tests the possibility of having extraneous data in the body as well. Now, you can implement these lots of different ways. I use curl to implement my SRTs, and I script the curl to also create output. You can use curl, wget, or any basic HTTP client, but I encourage you to use one that is a command line client. Don't get too tied up in UI at this point in the game. Just write some tests that you know you can call from the command line and repeat over and over again. It's important to be able to pipe the output to a file so that you can review that, because you'll actually have hundreds of tests after a while, and you want to be able to check the results into a repository, allow other people to review them, and maybe even use them as part of your build pipeline. So when you review the results of these tests, you want to see, does the test succeed or fail as expected? Some you expect to fail, remember. And does the returned resource contain all the expected elements? If I ask for a user record, do I get the name, the first name, the last name, the address, the telephone, the email, so on and so forth? Are all the expected elements there? So it's really important to focus on all those things. We want to inspect both the input parameters and the output responses. We want to create some kind of simple scripted form that we can store for later. And we want to overall just validate the behavior of the API itself. So with that in mind, let's take a look at a working example of testing APIs. We're going to see SRTs in action. So for this module, I created a welcome API. It uses the same kind of approach that we've been using for all our other styles, but I added the ability to add, update, and remove, as well as list welcome messages in this API. I created a series of happy path tests where I want to test and make sure all these things actually work as expected and return some kind of 200 OK or 201 create or something like that. I also created a list of sad path tests. Actually, I have more sad path tests than I do happy path tests because there are lots of possibilities I need to test. And we'll take a look at those briefly. And then we'll take a look at the test output. I'm piping the output to a disk in this case, and then we can review that output later to make sure we understand what it's doing and what it means. So with that in mind, let's go. Okay, let's take a look at testing the API using the SRT approach. So first of all, let's just take a look at the actual API so we can get a sense of what that's like. I'm going to zoom in here a little bit. This should look pretty familiar to the other examples that we've looked at earlier. The interface looks a little bit more involved because I'm taking arguments, I'm doing posts and puts and deletes and that sort of thing. So you can see there are several places where I check results and return an error, status 400 or status 500 if I'm having a disk problem. And we're going to be checking for this kind of response when we get to the point of actually testing this API. Now I kind of built this up along the way. We've got get and put and delete, all the items we're going to need for a basic kind of API. So that's fine. Now let's take a look for a second at the code for my testing client. So as I mentioned, I implemented an SRT using bash and curl. So I've got a simple case where I take a couple of arguments, such as the default list of scripted URLs, whether or not I'm using an out file, and so on and so forth. So here's our example. We get start the service running using an npm command. So that makes it really easy. I wait a few seconds to make sure it's up and running, and then I simply go through the list of requests whether it is a standard output or it's piped to a file. And then the job is done. So it's a pretty simple approach. I'm using some extra details in curl. You can take a look at that yourself, or if you're using wget or some other client, you can kind of fancy things up here. But I just kept it real simple to get started. All right, so let's quit out of that. Let's take a look now at our happy path tests. So these are the tests that I expect to return 200. So that's the root, the welcome list, adding to the welcome list with a post, getting a single item, updating that single item, deleting that single item, and then here's adding to the list with an extraneous argument, which should be ignored, and it should work successfully. So that's my list of tests. I might be able to come up with a few more, but that gives us sort of the basic idea. The sad path tests are a little bit different, however. So I want to make sure I get a proper reaction when I attempt to get a resource that doesn't exist, or if I attempt to create one without arguments or with an insufficient number of arguments, or if I try to edit one with an insufficient number of arguments, or if I try to edit one that doesn't exist, or if I try to delete one that doesn't exist. And you can see how you can think of even more and more examples of how to do this at some other point. But for now, let's come up here. What we're going to do is we're going to do our little testing here. And for the first example, let's do the happy path. And we're going to pipe this to a file so we can take a look at the results a little bit more directly. So here we go. We're going to run the script using the happy path URLs and save that to a file. And I'm just going to run it. It just takes a couple of seconds to get it completed. And then we can go ahead and take a look at what the SRT happy looks like. So here we are. We started the API and we started the run. And here's the example. The home gets a status 200. The call to the list gets the 2 items in a status 200. There's the post example. There's the single read. There's the edit of that record. And there's the deletion of that record. And there's that one where we ignored the output and still created a record that we wanted. That's a really good example of the output that we needed. Let's take a look at another one where this time we're going to run the sad case. We're going to do the same thing using the sad script, and we're going to send it to an output file. Same kind of format, only we've got different tests this time around. Let's take a look at the results, and same thing. We started up the service, and we waited, and then we started our request run. So lots of these examples are going to return 404. Here's one where we're missing an argument. Here's another one where we're missing an argument. Here's a case where we attempted to do a put, and we're missing arguments. We're a couple of different examples there. Or we're trying to edit a record that doesn't exist. There's a 404, or delete a record that doesn't exist. And again, there are lots of other possibilities as well. But the key to all of this is this notion that now we're scripting our tests, and they're really easy to run. They take just a few seconds, and I can use these tests while I'm actually building my API in order to make sure that it has the interface that we expect, and that's writing SRT tests. All right, let's review what we've learned in this module. The goals of API testing are to validate the interface, not the code. We're going to use simple request tests to validate our APIs because they're easy, they're scripted, and we can store them for later. And we looked at a working example of an SRT set of API tests that we implemented using Bash with curl. And that is testing your API. Okay, now let's talk about securing your APIs. And we're going to take this in 3 steps. We're going to talk about API keys. Are you allowed to be here? Sort of the where of the API security system. We're going to talk about authentication. Who are you? That's identity. And then we're going to talk about the what. What permissions do you have? And that's authorization. So let's get started by talking about API keys. So are you allowed to be here? Do you have an invitation? Sometimes I refer to API keys as an invitation. Here's my card. I'm allowed to use this API. API keys are invitations to start using the API. They don't identify the users, by the way. They just identify the fact that you have received an invitation. So don't try to use API keys as identification. Don't use them to try to identify users. It's really insufficient. In fact, API keys are great when you don't need to know about the users. Maybe you're offering just a postal code list or a simple lookup table that anybody could have access to without identity. But they still need an invitation. They still need a key. Keys are also not permissions. Don't use keys to decide whether or not somebody can write to an API versus whether they can just read the API. So they don't contain access rights. Now let's talk a little bit about the mechanics of API keys. So you typically provide approved users a key for your API with some kind of register page. There can be a generate key function in your current service, or you can have a third-party service, depending on how sophisticated you want to make the process. The idea behind this is to make sure that you're only offering invitations, keys, to the people you really want to have them. So once a client gets a key, or somebody gets a key, that client uses that key in every single call to the service, typically in an HTTP header, sometimes as a query string, even sometimes as the body of an element, but that doesn't work all the time. The best one is to use an HTTP header or some other kind of metadata, depending on the style you have. So once clients send that header, servers then validate that key information against the list of valid keys. Maybe that's kept on a registration server or in some of the database or list or something like that. Now this is really important because you can revoke a key. If you find you've given someone an invitation and they've invited all their friends and you really didn't want all of them to show up, you can just take the key out of the valid list and that key no longer works anymore. So that's really handy. So let's take a look at how we can code API keys in a simple demonstration API.
All right, let's take a look at how we would set up API key validation for a minimum level of security. So random people can't just call your API unless they have a key. So here's an API, a little welcome API. This looks very similar to the other APIs we've been working with. And notice I've got a line here that loads a little library called Validate Simple API Key. This is just going to take a set of UUIDs, and you can either generate one or use one of the pre-built ones. So that's our API key validator, library for validating. Now let's go down and take a look at the calls. You'll notice here I've got a home resource and a generate API action. Neither one of those are secured, so I can get to the home and I can get to the generator anytime I want. This will actually generate a key and remember it. In this example, it's very simple. It only lets me do this in memory and it doesn't retain them. We're going to keep it super simple for now. And I've commented out the ability to list the API keys because we don't want just anybody to be able to do that. I do that sometimes when I'm debugging. But here's where we have our protected routes, the actions that will need validation. So when I get the welcome element, that's going to need a validator. So I'm going to insert the validator in the express line here. And when I want to post a new welcome message, I'm going to need to validate the key. And when I want to read one of them, I need to validate the key. So you get the idea, right? When I'm going to update one with a put, I'm going to validate the key. When I'm going to actually delete an element, I'm going to validate the key. So every time I do a request, I check to make sure that this request contains a valid key. Well, how do I check for the key? Where is that going? Right here. So let's go over here. And let's look at that simple API key library I told you I built earlier. Here, just to make it easy for us today, I memorized a bunch of keys. I generated some keys and put them in as an array. We'll be using one of these keys in our test. Typically, I wouldn't do this in production. I would just make sure that they're generated. So here's a generated one that uses a function that generates random UUIDs. And here's the validate routine. Basically, it looks for a header. You can see here that it looks for this header that says API key right there, and goes through the list of keys that I know, ones in my memory. And if it's true, then
I'll allow them to go forward. If it's not true, then I kick an error message that basically says it's a 401, it's an authorized, missing, or invalid key. And this is just a little routine that publishes that interface for the Express engine to use. So that's really all there is to it. That's actually pretty simple. So let's see how all this works. Let's go ahead and run our little routine, our little welcome routine. And then we're going to go over here. And what I'm going to do is I'm going to actually call up a little test kit. We've seen this testing earlier. So here are my little test routines that should all work. And notice that starting after the first root one, I include an API key header in every request. So that's the post, and that's the put, and that's the delete. This is just an extra test. But notice I've got an API key for each one of those. If I didn't include that key, this script, this test set would fail. So let's go ahead and go out here. And let's actually run the set and then get the output, and we'll take a look at it here in just a second. That was pretty quick. Now let's look at our output. And notice that the first one is fine. Gave us a status of 200, a response in the 200. Here's the one that's actually passing the key, where I get the list. This is one where I get to create a new one. This is one where I get to update an existing one and delete one. And that's really all there is to it. Now, if I just go back here and pick up this item, and I'm just going to change this key slightly, a little X in front of it. That means it's an invalid key. What we're going to see when we run this test again, we'll get the first one, right? Because that wasn't secured. But the second one is going to give us a status of 401 because it's either a missing or invalid key. This is a way that I can actually make sure every single request has at least some kind of validation check. You've got to at least be able to get an API key for me in order to use my API. And that's how we can set up API key validation for our web APIs using Express. Okay, let's talk about authentication, the second step in the three-leg system. So authentication is about who. Who are you? Identify yourself and prove you really are who I think you are. You can use authentication to establish user identity to make sure you know who they are. This is very different than the keys we talked about earlier that just identify the API. Now we're identifying the user of the API. Now it's important to rely on shared non-local identities, a third-party service, so typically a provider of identities. You can think of them as your Google login or your Facebook login or your GitHub login, or you can create your own provider for identity yourself. Most organizations have some kind of identity access management system already built. But it's important to make sure that the identity is not part of your API or your service. Make that a separate element. Now, OAuth is a reliable API authentication protocol because OAuth doesn't require the service to know the username and password, just to recognize valid tokens from an OAuth provider. And in this case, since we're doing APIs, we're going to use a thing called a machine-to-machine authentication flow so that we can do that without some human actually typing in a username and password along the way. So what are the mechanics of authentication in its simplest form? As I mentioned, select a third-party identity server to manage your identity. You can use your own OAuth provider inside your organization. We'll use Auth0 from Okta as our OAuth provider for these examples. Then you register that API that you want to secure with that third-party provider. That means that you provide some metadata about the API, and then this will help produce keys, secrets, and other information that users can access when they're trying to log into the API. So when clients want to call the API, they do this login with the provider. They pass the client in secret and some other metadata, and then they get a token, a valid temporary token from the identity server that then they use in every API call. And it's used as the authentication header.
So that is the process of setting something up. Let's take a look at how this works in our example API. Okay, let's take a look at securing our API with OAuth. First, let's take a look at the code. So here's the same welcome API that we've been using quite a bit, and you'll see right here, we've got this thing called JWT check, which is a token check. We got these values from the Auth0 website, which is hosting my OpenAuth services. We'll take a look at that in just a second. But I know what my audience is. That's my target. That's the app, really. The base URL is what the Auth0 thinks is my URL for all of their data. And there's a little signing out algorithm. So where did this come from and why is it here? Let's go ahead and switch over to Auth0. Now, I'm not going to go through all the details here. There's some links in the content that'll help you find some details on generating your headers, your client ID and client secret. But the important thing here is to figure out that we're looking at this API fundamentals application. There's a moment when I need to get a token for accessing the services. So I pass the client ID and client secret, which is registered with Auth0, and Auth0 sends me back this really long token. That token is life limited, and it's for using with calls for our application. So if I want to send a request, say to the root, then I use this header authorization, and I use that same token that was passed earlier. Now this can get a bit messy in the beginning. What I need to do at the start of the app is get a valid token and then use that token over and over again. There are a couple of different ways to do that. We'll get back to that in just a second. So now bear with me. So we've got this idea of a client secret and a client ID handed to Auth0, which then gives me a token. I then include that token whenever I make a request. So in the application, all I need to do to get that started is say app use JWT check. Use this structure value, these constants, to always check every single request with the service. That's built into Express. So that's pretty handy. That's pretty good. Now let's move on to the next step. Now here, what we want to do is get that service up and running. We'll get that started. So now that's started and it's ready to start checking authentication for every single request. Now let's go down here and move over to this corner. Now, if I just simply do a simple test here, HTTP localhost 3000, that's the root, and I don't send any additional information, I'm going to get an error, right? So that says it's an unauthorized error. Now, what I can do instead is I'll take a little script where I'm actually using the same service here, and that is the client service. So now here's that first example of an unauthorized request, and then one that's authorized. Again, I've included the authorization header that I got from Auth0 just a moment ago. So now what I can do, and for the second one that's authorized, you can see I actually got data back. Now, again, that's still a little cryptic. So what I'm going to do is go over here and show you something else. It's a little bit different. I'm actually going to use a tool called Hyper. This is a nice sort of command line application that lets me manage things like security in a much more usable way. So I'm actually going to load credentials into Hyper. Then I'm going to list all the credential information that I've set up for the Welcome API through Auth0. This is the one we've been working on. And you can see I've got the client secret, audience, the base URL, a whole bunch of information. And there's a spot there for the access token. That access token is what we're going to fill in right now. So I'm actually going to do OAuth generate a token using the welcome data. And that's going to generate that information. Now, how do I know that it happened? I take a look in there, that token is there. So now this is going to actually be quite easy. All I need to do here now is actually say go HTTP localhost 3000 with the OAuth profile of welcome. So now I'm referencing all of that OAuth data and I get the answer back. Now, if I did it without referencing the OAuth data, I would get that 401 that we saw earlier. So there are lots of ways that you can program around on the client side how to make sure you supply this information. We've just seen one example here. So we've got this notion of using a client that's aware of OAuth, or using a simple client such as curl, which means you just have to manually insert the header. And we've looked at how we modified the actual application to check on every single request through the use of Express API. And that's how you can use authorization and authentication with Web API. Okay, we've talked about API keys and authentication. Now let's talk about authorization. Authorization is the what. What permissions do you have for this API? I know you have an invitation. I know your user identity. What permissions are you assigned? So you can use authorization to handle user permissions, and that gives you a sort of a fine-grained control. Yes, you have permissions, you have an invitation, I know who you are, but you're only allowed to read data, not write data. So that can be one example of using permissions. Now, it's really important to rely on local permission validation. Remember, I talked about non-local shared identity. Now we're talking about local permissions. Your service should check the permissions of every identity that comes to try to do some functionality. We'll talk about how to do that. That means that your service is responsible for permissions. The OAuth service is responsible for identities. Permissions are usually shipped in a JSON Web Token, or JOT or JWT token, and that's a reliable access control token. You can use JOTs to carry permission data as well as some other metadata if you need it. We'll focus on permissions in this example. So how does this actually work? You add permissions to the registered API identities. Each user has their own set of permissions. We'll show you how you do that. When a client logs in, they will get a permission token back. The JOT token will contain all the permissions needed, so that when servers get a call from a client application, they can look at the JOT token and make sure that it has the permissions they're looking for. Note that here in this example, in this diagram, the validation of the permissions happens locally. It doesn't involve the identity server. It's just a local check. Now, sometimes that check can be done directly in the token. Sometimes that token points to a claim. We'll use the simple direct token access for our example. So let's see how that works, adding permissions to our working example. All right, let's take a look at how we're going to start supporting authorization or function level permissions for our HTTP API. Now, the first thing we need to do when we set this up is we need to go back to the auth0 site where I was defining my OAuth token and actually set up the notion of support for some permissions. So let's do that first. Let's go over here. So this is me logged into the auth0 site for the API fundamentals example API. You saw how I did this in the authentication section. Now I'm going to focus on permissions. And notice I defined 3 kinds of permissions: the write permission, the read permission, and the delete permission. So these are the 3 permissions that my API is going to support and that my logged in users will have to be given access to. Now, what's going to happen is every time somebody logs in, authenticate, we're going to make sure that they have the proper authorization. Now, how do we do that? I'm going to move over to another part of the auth0 site where I'm checking out the API details. I'm going to say this particular user is authorized for the API fundamentals. We saw that before, but now we're actually going to add a little bit more information. And we're going to include which permissions they're actually supposed to have. So this is the authorizations. They're authorized to write and authorized to read. So I'm setting up which permissions are going to be in scope for this particular user of the API. So now I've done the details. I've defined the permissions. I'm going to apply them to a user. Now we're going to go over here. Let's take a look at what happens next. So let's take a look at our source code and see how we're going to support that notion of permissions. Now, you saw before how we added a security layer when we were doing authentication. So now we're going to add the authorization layer. So this says that we're going to also support the notion of required scopes. Now, how do we support that? What we're going to do is say, for example, when you want to get the list, we're going to say before you have access to get the list, show that you have the welcome read authorization. So you've got access rights for welcome read. And the same thing goes for post. We're going to make sure that you have access for write. And then down here for get, we're going to make sure you have read. For put, we're going to make sure you have write. And if you try to delete, we're going to check and see that you have access controls for delete. So that's how we're adding that into the source code. So when we run this application now, every time somebody makes a request, they're actually going to check that authorization information. And that's going to be in the permission section. So let me go ahead and zoom this back out here. And we're going to actually just go ahead and start this up now. So now it's running. Let's move over here. Same thing. Let's take a look. I'm going to be using hyperscripting because hyperscripting actually makes it really easy to deal with OAuth tokens. I can load my tokens. We defined this in the previous example for authentication. We're just going to generate the token for the welcome API, and we'll be able to pass that back and forth automatically. Keeps everything really, really simple. So when we start, we make the first call. You may have noticed we did not ask for permissions at all at the root URL. That's pretty common, to make sure that the root URL is open, because that kind of points people in various directions to documentation and so on and so forth. But if you want to get the actual list, you're going to need to use your OAuth token. Now we're going to assume your OAuth token is going to have the read permissions in it, and that'll get rejected if you don't. If I want to add a new record with a post and a body, I'm going to be using that token. I'm going to assume from this angle that you've got the right authorizations in your token when you logged in. So that's how that's set up. So let's go ahead and exit out of there. Now let's just do a real simple run of this. We've got the API up and running. Let's go ahead and run our routine. And sure enough, everything works the way we expected. We had both read and write permissions. So I was able to get the list, go to home, get the list, and then add a record. But here's the trick. Let's go back now and take a look at our scope here. I'm going to turn off write permissions for this API, for this user. So now this user does not have write permissions, but they do have read permissions. So now let's go back and run the exact same script again over here and see what happens. And sure enough, when I try to write a record, I'm getting insufficient scope error. I do not have the proper permissions. So I know my permission system is working correctly. So there's an example of how I can set up authentication and authorization for the same API using OAuth scopes.
Okay, let's review. We talked about three things in this module: checking invitations, authenticating identity, and authorizing actions. The check invitation step is the where step. Where are you allowed to go? Do you have an invitation? Do you have an API key? The next step is authenticating identity. That's the who step. Do I know you? What is your identity exactly? And let me see if you're allowed to be here with that invitation. The third step is authorizing actions, the what step. What permissions do you have? Are you allowed to write? Are you allowed to delete and read, and so on and so forth? And those are the three steps: invitation, identity, and actions. And that's how you secure your API. All right, let's go from the ground up. We're going to build an API from scratch. That means we're going to go through all the processes we've talked about in this lesson so far and do it in a straight line. We're going to design it, which means we're going to create our API story and our description. We're going to code it. We're going to convert that documentation of the design into actual code, and then we're going to run it. We're going to turn it into a live API by looking at testing, security, and other elements. So let's get started with designing our API from scratch. Now, if you remember from previous lessons, we talked about three key elements: the story, the details, and the actual diagram. So let's start by writing our API story. Who wants to do what? What is the information that we need at a simple, straightforward level? Remember, we're going to create an API story document that has a simple purpose. What does this API do? Why do we have it? It's going to list the actions, the operations this API supports, such as share and edit and read and write and so on and so forth. We're going to talk about the data properties. What data does this actual API handle, such as ID and email and given name and family name and so on and so forth. And then what, if any, processing is done at the interface level to create valid IDs or that sort of thing. What other elements are there to the story? Now, we saw an API story earlier. I typically just do these as markdown documents that can be read through GitHub or Bitbucket or other places like that. And it's pretty simple, it's pretty straightforward, and it just looks like a narrative document. You can do these in lots of ways. You can have a template in Jira and so on and so forth. Let's go ahead and just look at editing up our API story document. So let's work on our actual to-do API story. Now you can see in front here, I've got a really simple document. I use this template pretty often. So this is going to be my to-do API story. I need to supply purpose, data, actions, and processing. So the purpose is, as we've talked about before, just a really simple statement, something that explains what this API is supposed to do. A simple command line app that will help people keep track of things to do. Now, this is a good way to make sure everyone kind of agrees on the reason we're doing this and why we're doing it. And it's handy in sort of as a reminder of like, what's the purpose that we're working under here? Now, the next thing is I want to actually keep track of what kind of data is going to be included in this API. So I say the data model is simple. There's a to-do record. They're going to have a unique identifier, a title, an optional date, and a simple format, and a status code. And I even list the valid values for that status code. That will come in handy in a little while. But now the data is not enough. I need to actually talk about the actions. What are the actions that people expect to be able to do with this API? So they'll be able to add records, update an existing record's title, change its status, set the due date. They'll also be able to list records and filter based on a few values like date, due, title, and status. Now, it's really important that I be pretty explicit here. Notice there are several things that they need to be able to do. This can be handled in lots of different ways once we get to the work of actually implementing details, but we're going to let those implementations play out later. Now, the other thing that I want to do is I want to include any processing, any rules, any things that we should be aware about. Unique identifier records, what happens if there's already an identifier on file, for example. There could be lots of things that end up in this processing section. But this is basically our story, our purpose, the data we manage, the actions we're going to support, and any other processing that should be considered at the interface level. That's the basics of creating an API story. All right, we're on to the next step. We've got a story document. Now we need to collect up all the details that are kind of hidden inside that story. We're going to identify all the data properties and action elements that we're going to need to mark up and deal with in our API. Typically, that means properties such as ID and name and address and email and all those other elements. What was named in that story and what else are we going to need that maybe wasn't named in that story? And we're going to talk about all the actions. That's part of our details as well. Read, write, compute, share, approve, deny, move, so on and so forth. All those verb type elements. We need to document every single one of those. Plus, almost every API has some kind of enumerations. Enumerations are the valid values for a particular element, such as a Boolean value can be set to true or false, or maybe a size value can be set to small, medium, or large, or status is pending, working, completed. These enumerators are very important because they'll need to be validated at the interface as well. So again, I typically just use a markdown document. It's not something really complicated here. I list the properties. I list whether or not they're required or optional. That's the R and the O. I talk about the general value of that. It's a string or a simple date or something like that. Notice in the actions, I will also use arguments as well. So the filter action can take a title or a date due or a status. Creating takes two elements, so on and so forth. And then I list the enumerations in detail as well. So that gets turned into, again, a simple document that just about anybody can read. And we're going to use that as our guide as we now edit our own vocabulary document. Okay, now we need to work on our vocabulary document. Properties, actions, and enumerations. These are the details that we need to know about when we're going to create our API. Now, I start with the properties because that's pretty easy to deal with. People think in properties quite often. It's the data points. It's the elements of the to-do records and their types and their status. Now, you'll notice I've got ID, title, date due, and status. Date due is marked with an O for optional. The other three are marked with R for required. So when I'm creating a record or editing a record, those are going to be required. I've also indicated simple string types for ID and title and a simple date format of year, month, and day for the date due. The enumeration list for status will add below. Status has only got a certain set of values that are valid. Now, data is pretty easy. It's the actions that get a little bit more interesting. So let's go down here and add the actions. Notice I'm going to list, I'm going to filter, create, update, and the status allows me to change the status, and the do action allows me to change the date due. Notice on filter that I notice that two of the elements can contain partial strings in order to match. Remember, we're doing an information query here. We're not doing a database entry. So we can have partial strings. And the status, of course, has to be enumerated. We've talked about that enumerator before. What is that enumeration really look like? Well, let's see. Let's just add this enumeration here. And notice that it says that status has three possible valid values: pending, working, and completed. Any other value is going to be rejected. So now I've got a decent vocabulary. All the property names, the action names, and the enumeration details. And that's the vocabulary that we need to design our API. All right, now we're on to the last step. We've got a story, we've got a vocabulary document. Now we need to complete our design by creating our ALPS profile semantics document that has all of those details in a usable form. Now, we talked about ALPS in a previous lesson. ALPS helps us focus on the design, not the implementation. We may need an open API spec or an async API spec further down the road, but right now we're still in the design phase. We haven't really worked out those details yet. And we're going to document three parts of any design. That's the ontology, or the data properties for that API. We know what those are. The taxonomy, the actual resources of those API, home, collection, list, so on and so forth. And the choreography, the actions. We've already documented the actions as well. When we combine those three things together, we get a workable API. And once we do that, we're going to generate a connection diagram that shows how we can navigate from list to item to create to edit and so on and so forth, because seeing is believing. Now, ALPS documents, as I mentioned earlier, are a bit fiddly. They take a little bit more effort. That's why I saved them until last. Let's make sure we've got agreement on our story and our vocabulary before we invest in an ALPS document. Now, a simple API like the one we have here, it only takes a couple of hours to create that first ALPS document. And it's really valuable because that's going to give us a visual of all the connections, how we can move from home to the collection of the to-do list, to the item of the to-do list, how we can set the due date, change the status, how we can filter and list, and so on and so forth. It's a bit more complicated, but it's very, very much worth it. Let's go look at editing and generating our ALPS document. Okay, now let's take a look at creating our ALPS diagramming and detail description document. Now, this is a template that I start out with pretty simply. It has the basics of whatever my description is going to be. The ALPS documents are a little bit more involved, but they work really well because they're basically the machine readable version of the vocabulary and the story document. So the first thing I'm going to do here is drop in the properties elements. Notice it's got ID and title and date due and status. There's some additional information on documentation and references. We don't need to worry too much about those right now. But that's the basics. That's our ontology. That's our property definition. The next thing I want to add is a taxonomy that talks about the resources, if I was going to do an HTTP API, or maybe the objects if I was doing an async API. So that'll be the next thing that I drop in here. Now, this has all the information about items and what's possible on an item. So the item has a to-do object, and has a bunch of possible actions. Same thing for the list and the home, as well as that actual to-do item that we were looking at earlier. So that's all set. Now we need to do a little bit more work. We've got the actual data properties defined and we've got the resources defined. What we need to do is connect them together, give them all a sense of how you navigate from one place to another and cover all of those supported actions that were in the documentation. And that's what we're going to do here. So now I'm going to go right back down to the bottom here and add all our actions. Now, there's my due date, my status, general update, create, how to get to an item, how to do a filter, and notice it says you can filter on title and date, due, and status, how to actually get a list, and how to actually get to the home page as well. Now, this gives us a sense of all of the details needed to actually create our diagram. This is a machine-readable version of the story and the vocabulary. And that's how we end up creating our ALPS document. All right, let's review. We talked about the importance of story, details, and diagrams. So first of all, we want to write our API story. That's the narrative. That's the prose that everyone can read and check and make sure that we've covered all the right elements, such as our purpose, our data, our actions, and any processing that that interface does. Second, we turn that narrative into a details document that covers our vocabulary, all of the individual data properties, all of the action names, and the arguments that they pass back and forth, and any enumerations that would define valid values for particular data processes. Then once we have that, we can actually go through the work of creating a connection diagram that shows how the API interacts, how we go from home to collection to list, how we edit, update, change, and so on and so forth. Those three elements, your story, your details, and your diagram, is how we design an API from the ground up. So now let's go on to the next step. All right, let's move on to the next step. We've designed our API using all our design assets, diagrams, and so forth. Now we're going to code that same API. Now we did our API story, our description, and our diagram. Now we're going to focus on converting all those design assets into working code. That's really the job here. And to do that, we're going to touch on a number of things. We're going to talk about how to use the ALPS document to give us the elements we need, the data points, and the resources and the connections. And then we're going to work through each one of those, the data properties, the HTTP resources, and the choreography, the connections between them. So let's start with just focusing on how we're going to convert this design document into code. What we're really going to focus on when we're writing this service is what data does the API handle? That's what we might call the ontology. That's the actual meaning of the elements like ID and status and given name and family name and so on and so forth. We're also going to create resources. This is going to be an HTTP API. So what state does the API provide? We have a home resource, we have a list or collection resource, we have an items resource. We may have some forms for creating new resources or updating existing resources. These are the actions as well as the elements. What operations does this API support? And that would be the choreography. That would be moving from step 1 to step 2 to step 3 and so on and so forth. These are all jobs we have to do when we create our API service. So let's just take a quick review. This is what our ALPS document looks like on the left, and this is the connection diagram or the choreography that it represents on the right. Let's quickly jump to the original source again, just to review what we did in the design phase. Okay, so this is our ALPS document. This is our ultimate design document. So there are lots of things going on in here. First of all, we've got the actual raw ALPS data. This is what we created. So this is the to-do list. We talked about the individual ontology descriptors. Here, we talked about the taxonomy descriptors for home and collection and item and
Then we've got the actual choreography. So we've got the goes and the do's, filtering, lists, items, creates, updates, status checks, setting the date due, etc. So this is all the raw information that we created with our Alps document. Then we get to render that document in a couple of different ways. So we get to see all the semantic descriptors in one place. For instance, I can just simply go right to ontology and see these are all the data elements, including the to-do object itself, which includes all of the extra information. I can also go back and look at the diagram and make sure that it's matching. Another thing I can do is I can check on the taxonomy. So there's the collection resource, the home resource, the item resource, and the to-do object that we were just looking at earlier. So for instance, the home resource has two possibilities. That's changing the state to refresh or to go to the list. The list resource is another one. That's the collections. So we can see that as well. And the collection gives me one or more items. I can go home, get the list, filter, so on and so forth. So that's all taken care of. And then lastly, we can actually look at the choreography, the actual connections between things. These are all the possible actions, and they all have consequence: creating, setting the due date, setting the status, updates, and so on and so forth. And that can be seen in the diagram that we were looking at just a second ago. So this is all the design elements. This is what we're going to turn into working code in our next step.
All right, so now we reviewed the design elements. We realized where everything is, how to find the data properties, the action items, and the resources. So let's focus on each one of those in turn. Let's start on the data properties, the ontology, the actual meaning of the data elements that we're going to share back and forth. So data properties, the first step is actually just naming them. They're the individual atoms, the ID, the status, the completion date or the due date, and so on and so forth. These are the actual properties that we're going to need to focus on. We also need to know about the data requirements. Which data properties are required or optional when creating or editing an individual to-do record? We have to establish that as well. Finally, do some of the data properties have enumerators? Do they have a limited set of possible valid values? For example, in our case, the status has an enumerator. So we're going to need to focus on that. So here's what our semantics to-do record looks like in the data portion: ID, title, date due, and status. And here is where we find it in code. We actually find there's properties listed, and there's requirement, and there's enumerators. So let's take a quick look at what that looks like in the source code itself. Okay, so we've seen this before. This is our Alps diagram for all the connections that has to do with the to-do list API that we were working on before. So what we need to make sure we understand is what the actual vocabulary is behind this diagram. Notice we've got a series of properties: ID, title, date due, and status, as well as an enumeration. And some of these are required. Notice it's required, required, required here. So when we translate this into code, we're going to need to take in both the connections and the actual data properties. To start with, let's focus on the data properties. So we can actually, using our Express framework, define the properties: ID, title, status, date due. We can mark which ones are going to be required, and we can actually say what the enumeration values for the proper values for status are. And that's all we really need to do at this stage to make sure that we're prepared to deal with this diagram and this set of vocabulary. So that's step one. That's the ontology part of our API. All right, we've started with our design. We've focused on the data properties. Let's focus on the next thing, the HTTP resources. Since this is an HTTP API, we're going to focus on exposing a select set of resources. And we discovered those when we're working on our design document. That's the taxonomy. That's the elements of the API itself. Let's take a look at what those are. Resources in HTTP APIs represent the state of the API, the resting places, the home page, the list document, the filter document, the item document, so on and so forth. So what do we have in our API? Well, we have a home. That's where the API begins. No matter where we are, we can start from the home place. We have the collection. That's where most APIs offer a collection or a list of items, possibly even support the notion of filtering that list to narrow the list a little bit. And then there's the individual items. Each item, the API has the ability to see a particular item and maybe edit that item or remove that item from the collection and so on and so forth. So those are the things we'll be focusing on. And in fact, that's what our ALPS document has already given us: a collection, a home, an item, and we've listed the actual to-do object as well. We'll take a look at that in our code. So let's quickly look at how the code expresses each one of these taxonomy items, each one of these resources.
So let's take a look at the taxonomy level or the resource level of our API programming. So what we're going to do is I'm going to load up here the resources folder in our project. Now, this will define all the resources that are going to be available. So there you can see there's the get to the root, there's a post to the root, there's the list, there's the filter. These are all the resources we talked about earlier. There's a read item resource, and there's a update and a delete. These are the basic pieces. There's a couple of patches for status and setting the due date. Remember, we had those as well. Now there's a trick in all of this. You'll notice there's an args action element. This actually ties the resource to local code in our application. So what happens when we want to do a status update? Well, we execute the status action. Let me go ahead and load the action file here, and this will kind of make a little bit more sense. Now there's the home action, which says it's going to accept a certain value and return a response. So let's skip down to the status one. Here's the status one we were talking about earlier. We won't go into all the details of the code, but this is the function that actually makes a change to the status. It takes an ID and an update value and properties and knows the rules about what's required and so on and so forth. So each one of the resource actions, such as doing an update or a delete or a create, is backed by some internal code function that does that very action. There's the filter action, for instance, or there's the list action, which is pretty simple, so on and so forth. So in our application, we actually have two important items here. That is the actual resource that's exposed to the router, and that's what we see here on the left, and the functions behind those resources internal to the application. And that's what we see on the right. So that's how we implement the taxonomy. We've got the resources and the actions to put them together.
All right, so we've exposed the data properties, we've listed the resources for this API. Now we need to make connections. We need to connect resources together with various actions. This is what we refer to as the choreography. Connections represent the possibilities of the API. They suggest flows. I can go from step 1 to step 2 to step 3. They're not necessarily the requirements, but they're possibilities. For example, what is the home resource connected to? Well, it's connected to the collection or the list. It's connected to the filter, and it may even be connected to the create action. What is the collection connected to? That could be connected to individual items, or the filter connected back to home. And then what is the item resource connected to? That's connected to the update action or the complete action or the remove action. And it also is connected to filter, collection, and home as well. There's actually lots of connections that happen between resources. We want to imagine the possibilities, what possibly could be connected to each other, and make those real. That will allow the client to establish their own workflow when they need it. So again, the collection, here's an example. The collection has home, list, filter, item, and create all as a possibility. And then we're going to express that in code. Let's take a look at the source code and see how that works. Okay, in this last step, we're going to do the connections part. We're going to connect the various resources and actions for those resources to each other to create our application. We saw this earlier when we looked at our choreography. When we look at the actual application, there are lots and lots of connections that we can make here, right? So what we're going to do is look at that list of connections and create that over here in our application. So let me just call up the transitions. This is what we call transitions, or the connections. The transitions file, which describes each of the particular connections. So there's a home connection, there's list, there's filter, there's the create operation, there's reading, updating, changing the status, changing the due date, and removing. These are all the various transitions that lead from one step to the next. And they have their href, they have their properties, they have the HTTP method, and so on and so forth. And it's through this that we actually connect everything together. Now we know we've got our data properties, we know we've got our resources and actions, now we've got things that connect them together. And that rounds out the set of translations that we have to do from our original design document to our working application. All right, let's review. This whole process has been about turning our design into code. So the first step is using that ALPS document and locating things like all the data properties, all the resources, and all of the actions or choreography inside that document. And that's exactly what we did. We found all the data properties, which were ID and title and status and due date. We identified the resources such as home and collection and item. And then we created connections between the home and the item and the collection and the list and all the other actions that we possibly could imagine that a client might do. Remember, what we're trying to do is make the connections real so that clients can establish their own path through this HTTP API. And by putting all those things together, properties, resources, connections, all through the design document, that's how we code our API from scratch. Now we're on to the next step in building our API from scratch, the run it stage. We've already worked on design. We've converted our API story and description into design assets. We've converted that design into working code. Now we need to turn the working code into a running live API. And that's what we're going to work on in this last step. And this involves two key elements. We have to test our API. It's not production ready until it's been tested. And we're going to create our tests using our ALPS and vocabulary documents from the design phase. We're going to focus on the design level tests. And next, we're going to secure our API. We can't put it in production if it's not been secured. And you'll remember we talked earlier about invitations with API keys, identities, and permissions. So we'll work on those as well. So let's focus on testing the API using the ALPS and vocabulary documents from earlier in our process. Now, you may remember the to-do vocabulary. This was a great handy document which listed all of our data properties, all of our actions, and any enumeration rules. This has almost everything we need, but not quite. The implementation detail has one more element to it, and that's the taxonomy. We've got the ontology and the choreography. We've got the data and the actions, but we've got to identify resources and objects that we're going to be sharing as well when we create our tests. So the ontology has all the individual elements, ID, title, date due, and status. We can get that directly from ALPS. These will be the values we'll be using when we create our tests. Now, we also need to know about the resources and objects. So there's a home resource, there's a collection resource, and an item resource. And the collection and item also have that to-do object, which is the details of that aggregated set of properties. So we're going to make sure that we test each and every one of these resources as to what's a part of these resources, what comes back, and when the resources have those objects, that those objects are correct. Finally, we need to test the connections, the actions between every single resource, moving from the home to the collection, from the collection to the item. What's valid in each step? Can I do a filter, a status, a due date check, or update at this particular stage? We're going to have to test all of those items. And you can see that's actually quite a few things to test. Now, you remember from earlier, we talked about using simple request tests to probe the interface. That's what we're going to focus on today. We're going to inspect the request parameters and response bodies. And we're going to script curl to implement these simple request tests against our API. And then we're just going to eyeball the results. Are these APIs behaving as we would expect? So we've got a set of tests that we can run using the ALPS and diagram information, and that's how we're going to put together our test. So let's go build a handful of tests for our new to-do API. All right, so let's test the code that we've been writing these last several sessions. We've got a couple of things we need to do. So we're going to actually use our testing platform, a simple request test, which we've seen before. We're going to put together some tests. These should all return 200. So they'll test the ability to go home, to get the list, filter, to create a record, to modify that record, to change its due date and status, and then to actually delete the record when it's done. So that's the script, and we need to get 200s from all of those. That'll be fine. Now what we need to do to come over here is the first thing is we're going to need to run the application. And now we're running it. Now let's go back over here, exit out, and let's actually run the happy path version and store the results in a log file. So everything seemed to work fine. We got all of the information that we needed. And we could actually, if we want to, inspect that log file. It's actually a pretty long file, but it gives us the information we were looking for. So everything seemed to work just fine, including even the delete operations. So that's a great first step. Now we also need to test the SAD path as well. So if I go along the SAD path, there are certain things I should not be able to do. I shouldn't be able to read a record that doesn't exist. I shouldn't be able to create a record that's missing information, so on and so forth. So that's the thing we're going to test now. Let's go back, do the same thing with the SAD path, and we'll save that results to a log as well. And again, same thing, only we get the 400 requests just as we would have expected. So now we know that the application is working because we've got our basic tests working. That's a really good sign. That's how we're going to make sure that the application we build at least meets the fundamental minimum requirements for our design. Okay, we got the tests built and they're running, so that's a great sign. We used the ALPS information, the vocabulary, and its diagrams to glean the ontology, taxonomy, and choreography information that was necessary to make sure we were testing the right things for our API. And then we used the simple request testing, probing interfaces with request parameters and response bodies. And remember, we had both happy and sad tests in our module that we made sure that we can also test the mistakes or the invalid elements as well as the proper one. That's testing our API. Now we've got one more step to make it production ready, and that is we need to secure our API to make sure we take care of invitations, identities, and permissions. That means we're going to update our API code with that information, and then we're going to write another set of tests that know about security to make sure that it's done properly. So let's take a look at adding to code. Now we're using the Express framework. It's pretty easy. We talked about this in the security module. To add, in this case, we're just going to add a simple API key requirement using the pipeline to insert a check for API keys for every single request. So even in this case, even the request to home is going to require a key. So all we need to do is update our code. Let's take a look at the steps we need to update our code to support invitations in API keys.
We've run basic tests to make sure that the application interface, the API, is working the way it was designed. We also need to test the security as well. So what we're going to do is we're going to run a version of the API that requires API keys. We talked about API keys earlier in the security unit. So now let's take a look. We're going to use the hyper utility again. You saw the hyper utility in our previous test. I like it because it's a little easier to put together. So in this case, we're just going to call this URL and just test and see if it actually checks for keys. That's all we're really trying to do in this test, to make sure that we know whether or not it's actually testing for keys. So let's do that first step. And we'll just say todo.hyper and see what the result is. And sure enough, it is testing for keys, because it gives us a 401 status, a missing or invalid API key. That's encouraging. Let's go ahead and look at a more involved script here. We'll zoom in a little bit here. So now this is a script that starts with that URL, but this time supplies one of the available keys. And now it lets us get a list and filter, add a record. So these are basically all the same kinds of steps that we were doing with our simple request testing earlier, but in a little bit more controlled format. And again, we're using the API key header, which is what we need to get through the security requirements. So let's go back here.
And now
let's run this, but we're going to run it with to-do keys. And it's going to be a long response, so I'm actually going to send this to a log file. All right, here we go. There are all those steps that we just saw earlier. Let's see what the resulting log file looked like. And sure enough, we've got lots and lots of status 200 information. So all of that ran as planned. So now we've actually confirmed that our security arrangement also works as expected. So we've tested and secured our app and made sure it's ready to run in production.
All right, the next step is to actually write tests to validate that our invitations are being tested and honored. And we're going to use a slightly different interface for writing the test. We're not going to use an SRT. We're going to use a command line tool called Hyper. This is a tool I created several years ago to do just these kinds of tests. We're going to create tests that pass the API key as a header, and you'll see this test is a little bit more verbose, and that makes it easier for us to see exactly what we're passing in every single request. And here we are, we've got a valid API key from our collection, and we're going to pass that each time we make a call to the API. And that's going to be key for making sure that we test whether or not API keys are valid and our code is acting correctly. Let's review what we've been working on. We had to test our API and we had to secure our API. When it comes to tests, we're going to use our ALPS design document and our vocabulary documents to help simple request testing to make sure that we've got all the parameters we need and that the system is built the way it was designed. When it comes to securing our tests, we're going to make sure that we add the elements inside our API interface code to check for identities and invitations and permissions. And then we're going to write additional tests to make sure that it also exercises all of that added secure information built into our API. And that is how we run our API from scratch and make it production ready. Okay, let's do a recap on the whole course. We've talked about the basics of APIs, the types of APIs. We've talked about testing and security, and we built an API from scratch. On the basics of APIs, we focused on three key things. Protocol. APIs rely on HTTP messages and methods to make information pass from client to server and back again. Understanding this message-based protocol is important. We also emphasize the use of Express.js to expose all our internal services to an external API. And then finally, we focused on this notion of leveraging client platforms such as browsers, command line interfaces, or dedicated applications in order to interact with those APIs. And then we focused on the notion of API styles. There are lots of styles, but we focused on 7. The asynchronous style, which is good for events, the GraphQL style, which focuses on data, the gRPC, which focuses on functions, the Hypermedia API style focuses on connections. We can use RESTful when we want to manage resource state, Webhooks for one-way alerts, and Websockets for two-way alerts. That's lots of possible styles, and each has its own strengths and challenges, and you want to focus on the ones that are going to give you the most benefit for your need. We also talked about the importance of testing and security. In the testing side, we focused on goals, the happy and sad rule, and SRTs. Remember, the goal of testing is to validate the interface consumers can see. It's the interface that we're testing, not the internal functionality. That's being tested somewhere else. Also, we had this notion of happy and sad path tests. Happy path tests test the 200 OK conditions. Sad path tests focus on the 400 bad request conditions. We need to have tests for both to make sure that everything's working properly. And we introduced the notion of simple request testing, SRTs, to validate the APIs. They're simple, they're scripted, and they can be stored for later in your project, in your pipeline, and used over and over again. They're a great way to see what consumers see when you're doing your tests. We also focused on security. We talked about this notion of invitations, identities, and permissions. We want to check invitations. Do you have a key? Do you have an API key to even be here at all? Next, we want to check your identity. Do I know you? Have you registered for this application, and do you have permissions to be here? Finally, we want to talk about the authorization of actions. Sure, I know who you are, but are you authorized to do the thing that you're about to do? Are you allowed to do that? Invitations, identity, and actions. And we turn all of that into code in our Express.js applications in this series. Finally, we built an API from scratch to bring it all together. We focused on design, code, and run. We focused on the API story, API description, and created a diagram that everyone can use to guide as we put things together. We then converted all of those assets of stories, descriptions, and diagrams into working code using Express.js and the Dart framework. And then finally, we turned that working code into a live API by testing and securing that before we released it. And then we tested it out, including all our security features. In this case, the API key is testing to make sure that everything is working properly. Design, code, and run. That's building from scratch. So, we've had a great time in this course.